Right, good morning. Welcome to Christchurch and welcome to NZNOG. We've put on the weather to remind you of the summer we all just had. Right, NZNOG 2026, just some housekeeping, regular stuff. In case of an emergency, follow the instructions of the staff. It's got the earthquake instructions there, but the reality is just follow the instructions of the staff. For some reason in Christchurch, they have quite good procedures for earthquakes and things worked out. There are defibrillators. There's one downstairs. They're downstairs. Again, just ask the staff. The toilets, if you go out to the escalator, but don't go down it, go round to the left, you'll find the toilets. And it's a no smoking building. Please go outside and away from the entrance at least. There is Wi-Fi, as you'd expect. Hopefully you've all seen those. Starting early, not everybody's here obviously, but there are 260 people registered. We often get to say this is the biggest NZNOG, but this year has been a particularly big jump. Right, we had a 30% jump. The biggest we ever had previously was just under 200, so adding another 60 people. A little bit of a surprise. Great, the community's expanding like that. Should point out that means there's quite a lot of new people in the room, a lot of people who haven't been to NZNOGs before, possibly as many as 1 in 3, don't quite know. So, we want this to be a community, so to talk to people, if you see somebody standing there, try and include the new people in the community, please. We also have, for the first time for a few years, real live actual students here this time, so, keep those good job offers in your back pocket and look for young people. NZNOG is a trust. It's run by the trustees. There are 6 of us. There's 3 more standing here. Do you want to stand up, guys? And Maria and Barry. Maria might be still out on and Barry's at the back. If you've got any suggestions, complaints, comments, feel free to come and talk to us. The trustees are the people who have the ultimate responsibility for making sure the conference happens. We appoint staff who have been excellent. We find sponsorship and put together the program. On that, there is an anti-harassment policy. It's on the front page of the conference, but it's linked on the front page of the conference page, I should say. If you feel like you need to make a complaint, the policy says in an email, but feel free to come and talk to one of the trustees as well. We're now becoming a more modern organisation, and we have actually joined social media. So, if you're on LinkedIn, feel free to link to our page. We've got, as well as a lot of attendees this year, we had more talk submissions than we've had for a very long time. So there's a very full program. We've got a bunch of really great talks coming up, and hopefully you're all as excited as I am for the whole conference. It is going to be a very full program. You will be pretty tired by the end of tomorrow, though. Tonight we are going to the Air Force Museum. The buses will be leaving here at 5:30. They'll be here by 5:15 to leave at 5:30. Hopefully get everybody there at 6 o'clock. There's drinks for an hour, mingle, socialise, and then the dinner service, and then there will be buses rotating, several buses, so you won't have to wait for a whole round trip from 9:30 on, but to at least 10:30 to get everybody home. We're not counting people on and off the buses though, so make sure you get on one. Finally, the sponsors are really important to us. Sponsors pay, this is now a $250,000 event, and sponsors pay for roughly 60% of that. So they're really important, and they're becoming more important because they pay for so much that all the extra registrations represent a bunch of extra cost that, to us. You're not covering your cost with your own registration fee. So the gold sponsors, NZIX, Nokia, and .NZ. Some of these guys have been regulars, and we really appreciate them. The drink sponsors, a lot of people were last night and heard from Ken from Davoli. Chorus sponsors tonight's drinks. Then we have a set of silver sponsors, Sienna, HP, Megaport, Mercury, Red Hat, and Veta. The dinner sponsor is Equinix. The lanyard sponsor, you will see on the lanyard, Flex Optics. CDC and Comtest are the lunch sponsors. ADRWS will have the energy drinks, is it tomorrow, is it? And Searchlight is the coffee sponsor that's had the long lines of 2 carts. There were 2 carts. The second cart will be here at morning tea, but not at lunch. And then we have some community sponsors. Mercury are having a phone giveaway. You should have received a tag in your bag with a number on it. Go and talk to the Mercury people and see if yours is a lucky number. You might end up with a new Samsung phone. Great. Sorry, that's the fast introduction because we were already starting late. Right, now we've got Cams from Akamai. That one's for the slides. This one's supposed to be a pointer, but I haven't looked at how it works. Yeah.
Thank you, kia ora. So thank you for giving me a chance to talk today. So I'm going to talk about the Akamai traffic flow. Yeah. So this is the, so my name is Cams. I'm one of the network architects of Akamai, and I do look after the Australia and New Zealand network. So you can come to me if you want to talk about more details later. And today I'm going to talk about a quick introduction of Akamai, our infrastructure, and how we do the mapping and some best practice and recommendation that to optimize your Akamai traffic. So a lot of people, I think, know that Akamai is a CDN company. That's true. But on top of that, we do have security, and we acquire a cloud company called NZNOG. So now we do CDN security and also cloud computing. And this is our infrastructure. So we do connect with a lot of networks here. So we deploy a lot of edge pop, and we do have more than 1 petabyte of egress capacity that we have. This is just a map of our global infrastructure. So you can see the blue dots, that is where we have the edge pop, and then we have our compute side, of course. And then zoom into New Zealand. This is what we have. So we have, our deployment is mostly by cache server. So we deploy in all the major ISP network inside their network. But we do have also our infrastructure pop. So in terms of location, we have, of course, Auckland, Christchurch here, and then Wellington, the capital, and then Hamilton, and also Tauranga. So we have deployed in most of the major cities here. And for infrastructure, we are mostly in Auckland. So we are in 2 degrees in CDC, Silverdale, and also in MDL. And we are actually connected to 3 of the major IX here. So we are in AKOIX, HIX, and Mega IX. We are able to map more than 95% of our user traffic, New Zealand user traffic, within the country. Yeah. So, and I'm going to talk about how Akamai works. But before that, I'm going to talk about in a very general sense on how CDN works. So, there are many ways to do CDN, but ultimately the goal is to map the user to the most closest edge pop. So because the closer, the shorter the latency, the less bottleneck, the higher the throughput. So, and different CDN have different mechanism. So for Akamai, we are using like DNS, and also on top of that, we are also using a lot of different network matrix, like our server resources, the latency, the bandwidth, server capacity. So we do take into a lot of account to see how we should map the user to the most optimal node. And for other CDN, they also have different mechanisms. Some are using Anycast. So they always send you at the same address, but they map you into different nodes. Some are using BGP. So depend on what BGP feed that you send to them, then they map the traffic to there. So there are always like pros and cons of different mechanism. But basically the CDN is to map the user to the closest edge port, or the most optimal edge port. So I mentioned that Akamai, we are using DNS. So exactly how? So we have so this is a diagram, a simplified diagram on how we map the traffic. So we have an end user, like a mobile user or a laptop user, when they do a DNS QE of a Akamai hostname. So they go to their resolver, usually the ISP DNS, and the ISP will go to do all the DNS recursion, go to the root server, go to the .com, and eventually we'll go to our customer name server, the authoritative name server. Then because they're using Akamai, they will be CNAME to one of our host name. Then from there, it will become our Akamai mapping, because from there will become a Akamai.com domain. So we get that information from the resolver, from the DNS resolver, so we know who are queuing the host name and what host name they're queuing. Then we can map the traffic to the closest node. Let's say we got a resolver from 2degree, and they are asking for www.akamai.com. Then we know, then we can, based on this pair, we can map the user to the closest edge port, and then we give the closest edge port IP to the resolver, and resolver give it to the end user. So from there, the user will send an HTTP or HTTPS request. So this is a very simplified, but the key is we are based on DNS and also based on what are the resources that you're looking after. So you have the host name, because different host name, that means different content, and different content, we put it in different cache node. So this is an example of our CDN mapping. So if you are a Oakland user, although you are using the same, so chances you are using a DNS in Oakland, or you are a Wellington user, then you use a DNS in Wellington. So you see that, you will see the CNAME is the same, because the customer is using us, and then they CNAME to Akamai hostname. But ultimately, the resolved IP will be different. So in here, that means a Oakland user using an Oakland DNS will resolve them into an Oakland edge port IP. And similar for Wellington. So it's a Wellington user using a Wellington DNS, given the same host name, we give them a Wellington edge port IP. So this is an example. So now on how Akamai works, we have more than that, I mean more than DNS. So there's some fact that I think for you to understand that, because I think a lot of here, you guys are network operators, so the way that you build the network is very different than us. So first of all, we are a very distributed edge port network, so we don't necessarily have a backbone connect to them. So we put cache server within an ISP, or even our infrastructure node, they may not even connect to each other. Because the way that we do is we just simply direct the user to the closest edge port, and we send traffic from there. And so traffic is always from our edge port, but it could be a edge port in your ISP, it could be from a public infrastructure port through different links, like for a transit link or for a PNI link. And then we map traffic based on DNS, and also there's a lot of other attributes that we have to consider, because if the edge port is full, is down, then we also have to map it to the next optimal node. So we classify our edge port into two major types, what we call private. That means only serve a dedicated user. Those are mostly inside the ISP. So we put it a cache server, we cooperate with them. The cache server inside that network is only served to that network user. And then we have some public cluster. So the public cluster will have the full internet access. So we have a transit link, we have PNI link, we have IX link. So from there, we send traffic to the end user. So depends on the network relationship that we have with us. If you have a cache node, then chances we'll be serving from the cache node, because we have a priority to serve from cache node first, and then we serve from a public cluster. So the user traffic is from the cache port, and then the cache port will have to get the origin content, because the edge port is a cache server, or more like a reverse proxy. So if you are getting a content, download a content, a movie, or doing live streaming, or just go to download software, then the edge port don't have that content at the first place. So what the edge port do is you have to go to the origin, the customer origin, to fetch the content. So For the very first user, then we get the content from the origin. But after that, we cache the content in the cache pop. So for the second and the subsequent users, the speed will be much faster because the content is already in the cache. So, and then we have a concept we call mid-tier. So instead of all 4,000 cache pop all go to our customer origin to overload them, we do have what we call mid-tier. So a Akamai cache pop will go to another Akamai cache pop first before you go to the origin. So for this, is actually number one is we are not overwhelming the customer origin. We also improve the performance because we have a second layer of cache aggregation. Now you come to my favorite topic on why if you do a lot, we want to fine-tune Akamai traffic. I mean, as a telco, as a network, most of you will do all different type of traffic engineering, and BGP is one of the most common one. So you do like ASPAR PPAN, you do MED, or even you do specific route. But chance is, because of our network infrastructure, it's just a distributed cache node. It's not a continuous network. So chance is those BGP traffic engineering probably don't work. But I will cover how what is a better suggestion later. So you think about that. Number one, we don't map traffic purely based on BGP because we are not a continuous network. So every cache node have their own connection, and depends on which cache node you map it to. So the connectivity to the end user could be different, because we also take into consideration of the cache node capacity, the bandwidth, and also different content will be on different cache pop. Now, you think about like the first, like AS path. I think you do, okay, now I want an Akamai cache node from A, not from B. So I prepend to A. But you think about that, you are actually prepending to different Akamai nodes. So because they are not continuous, so we don't see the AS path prepend if you are prepending in a different node. Because you have a different IX connection to us, but to us, it's actually two different nodes. So AS path is chance is you are prepending into a different node, then it don't matters, because from that node, we see no matter one AS path or two AS path, we will send the traffic to you. So the first thing is we map traffic to the optimal node, then BGP come after. Now the other scenario is, I think a lot of people use do MED. It only works if you are connected to the same cluster as us. So we do honor MED, but only if the links are on the same cluster or same router. But in most of our case, because you are probably connect to us in different ways, and you do MED in different IX, in different location, then it don't works. Now, it's also come to specific route. I think a lot of you also do specific route because you want to do traffic engineering, control traffic on different links. But on Akamai, because we take the prefix, the host prefix, because we don't, it's not, again, it's not continuous network. So a cluster see a SAS23, it doesn't see the SAS24 on other clusters. So if you do specific route, sometimes you will find that it's not working. And even it works, it will take some time for our mapping system to react. It's not just exactly BGP. So in the conclusion is that, so we actually map traffic based on DNS on top of BGP. So BGP only happens on the router, that connect to you if this is on the same router. But other than that, we are mapping you into a different cluster. And so that's why the normal BGP technique don't work. And we do also have different preferences on our mapping system. So we prefer a on-net cache node inside the ISP first, because this is where the closer to end user, the better the performance. And then we also dig into like the network latency, the content policy. So there are many different criteria when we have to choose the most optimal node. Now, given that all those BGP don't work, I do have some suggestion. I mean, if you want to optimize our traffic, so I'm going to share some best practice and recommendations. Yeah, but of course, you can always talk to us. You can open a ticket with our, send an email to me, or open a ticket with our network support team or our NOC. They will be able to help you. So first thing is, I would suggest that you set up your own resolver, because as I mentioned before, we do map based on DNS. So it's better to have your own DNS resolver. I think a lot of ISP, you guys to have. And I also recommend that you do it as a distributed way. So you have let's say you have DNS you have users in multiple cities. I would suggest that you also have DNS in multiple cities, because we do see the DNS IP as one of the mapping element. And if you can't set up your own DNS, I would also suggest that you try to use Google or OpenResolver as OpenDNS, because we do have ECS enabled with them. So we can see the end user IP, then we map based on the end user IP. But this is not very optimal because we can't measure the performance. We also suggest that you publish your end user or your IP location through the standard RFC 8805 format, so that we can see if in case we map based on end user or based on your user prefix, we know the location, so we can based on that information to map traffic as well. And also maintain a good performance to your DNS resolver, because sometimes we do performance check to your DNS resolver to measure where is closer to the DNS. So I mentioned that there's so many traffic engineering techniques that don't work, but in order for us to work, it's better to send a complete and consistent prefix to us. So if you are peering with us, then I would suggest that you send us all your prefix and in a consistent way. Then we'll be able to send the traffic consistently. Otherwise, you send me a DNS prefix here and a user prefix there, then I will not able to map traffic all on the peering link. But if you have a problem with a specific link, we can do some fine adjustment, but maintain a consistent route alignment is quite key to us. Also, if you are a transit provider, I would suggest that you also suggest your downstream to send your complete end user the prefix to you, so that we can have a complete routing path to you. Do not filter traffic, because we do measurement. We do a lot of latency check on which cluster is closer to end user or closer to the DNS. So I suggest that if you better not to do any filtering, and if you send us a session fee, I would expect that you're able to we are able to send traffic to the host session fee, because chances our router don't have a full routing table, and we do a lot of performance check. But if you have a security reason, you do ICMP limit, or you do specific firewall, do let us know, so that we can work it out on what's the best way to monitor your network. And also avoid carrier identity, because end user prefix of 100.100, it doesn't meaningful to us. We don't know the location, we don't know what's the AS number. So if you have a cache server, you do put us outside the carrier identity network. And traffic is moving to V6, so I would also suggest that you enable V6 with us, no matter on a cache or on a peering, so that we have the BGP information, so that we can send you the V6 traffic. And I'll cover more about on the next slide about our V6 traffic as well. So this is an overview on what we do. We do a lot of measurement, so we do know the IPv6 percentage that we observe from our network. So in New Zealand context, we have seen about 23% of IPv6 enabled user, and pick some of the major ISP here on what are the V6 traffic that we observe, or the V6 adoption that we see. So 2degree is the highest here, with 33%, and then followed by Mercury, One New Zealand, and Tifoli. Yeah. So you can see this on our website. We do publish that on our website for the IPv6. So in summary, Akamai, we are a connected cloud. We do more than CDN. Our network is a very distributed edge port, like globally. And most of the traffic engineering BGP traffic engineering don't work, because chances you are not doing it on the same cluster or same router on our side. But we do suggest that you could set up your own DNS, you send a consistent prefix, all sort of practice. Hopefully it will help give you some insight on how Akamai works, and also how to fine-tune your traffic. But at the end, if there's still any problem, do come to talk to me. Here's my contact. And then if you want to peer with us, here is our PingDB information. Yep. So I think that is my presentation. Thank you. So open for questions.
Hello? Any questions for Cams?
Hi, Jeff.
Hi, Jeff. Jeff Houston, APNIC. I was listening to a talk about the way YouTube do their streaming. And of course, they block the content, it's a lot of content, into chunks. But then, just to make sure that they've made the right choice, they occasionally dither the service across to nearby servers to see if the original choice was poor compared to alternatives. For example, you could be in Japan and get most of your stuff delivered from Osaka, but you notice 1 in every 10 or 20 chunks will come in from Tokyo. And if you're actually closer to Tokyo, it'll shift. So that it doesn't take the original geo choice as Bible, it's constantly checking whether it made the right choice, which in the case of really big volume streaming content is important. When Akamai makes a choice based on the assumption that you live close to your DNS resolver, cough, cough, do you ever revise that choice for big content, or you just stick to it and deliver come what may?
So I think for, let's say, for live streaming event, then that's the content, I think no matter YouTube or most of the streaming platform, is actually a lot of different large chunk of file, like 10-second segment. So for that, we are also doing that dynamic mapping. I mean, if there's problem, let's say a Tokyo user, they normally get it from a Tokyo customer for that continuous video stream. But if that is a problem with the Tokyo or the link is full, the server is full, our TTL is only 20 seconds. So the DNS will change it to other customer. I mean, in the next 20 seconds, after TTL expire. So the Tokyo is full, then we map them to Osaka. Is that, I don't know whether is that answer your question, but.
You're relying on the DNS to actually change where the server is.
Yes.
That's a brave engineering choice, and let me congratulate you for your courage.
Yeah, but on top of DNS, we also measure other factors. Yeah, so.
I think maybe you should have gone through the other methods that you're using, other than just the DNS, obviously.
Yes, so again, DNS is the primary factor, but we do look into latency, network performance, customer content, policy as well. So we never congest a link in a way, because we know a link is full, then we shift traffic to other customer.
So on that note, like I hear complaints from time to time where ISPs find traffic coming in from Akamai over expensive links, and they think they've got cheap links to Akamai and the traffic should be coming in there. Now you're saying we should never filter traffic, but like other than contacting you, that's the only way really to stop traffic coming in an expensive international link? There's no real other way once Akamai decides?
So I think the question is because the ISP, your expensive link, like your transit link, probably that provider could be my peering link. So the way that I see a link could be different. But again, if you don't prefer a specific transit link or expensive link, we could try to filter that on our side and then try to shift other links. But provided that we do have other links to send, right? Otherwise, we send that out of the country.
But I think your summary is really you want to be filtering that at your end, at the Akamai end, and you don't want ISPs to be filtering that on their international link, for example.
Yeah, we can do both. I mean, if you withdraw, but the problem is with a transit link, we take it to full out anyway. When if it is, or if your upstream is my peers, we take whatever they send to us. I don't know whether it, to be honest, I don't know whether it costs you a lot or it don't cost you much. Because for me, if a peering link that we treat them like free, for example, but that could be your upstream. I understand that. So yeah, but if you have that kind of problem, just again, let us know, because I don't know exactly your arrangement with other ISP, I mean, cost-wise. Yep.
Cool. Any other questions from the room?
What about EDNS client subnet support for other resolvers other than Google and OpenDNS?
So we do, good question. So we do support for any ISP, but there's a process to do that. So we have to manually whitelist your DNS resolver. Yeah, so again, talk to us and then we can whitelist your DNS server to enable your ECS. Because let's say you have centralized DNS in Auckland, but you have user in Queenstown, in everywhere, then we can do ECS, but on an individual case by case.
Great.
Any other questions?
Okay, thank you
Okay,
very
thank
much.
you.
Okay, and the next speaker is Claudio from Arista, who's coming to talk to us about overlays.
Thank you very much. It's great to see a big crowd. I presented here in 2019. I think it was in Napier, and 30% less people at that point in time, so quite amazing. I'm Claudio Captari. I'm the Systems Engineering Manager for ANZ at Arista. I'm based in Melbourne, and I'm here to talk to you about the comfortable complexity of network overlays. Traditionally, the carrier core, the data center, campus, and even the WAN services have been managed as separate, isolated domains, each with their own set of protocols, management tools, and complexity. Today, we will look at a different approach, one in which we look to unify those architectures. And look, through the concept of comfortable complexity, I'm acknowledging the fact that there is a level of sophistication to the topic. But from our perspective, our goal is to make things simple, have that single unified overlay architecture end-to-end. The big clicker, let's see which one is that. This one. Perfect. All right, so I'm going to start with the complexities that we are seeing across the routing domains. And I spoke about the fact that I'm going to address a multi-domain architecture. And if you think about the data center, the campus, the carrier core, the branches, all of those are different snowflakes, as I mentioned, and they are treated very differently from each other. And at the end of the day, they require a bespoke skill in managing those environments. And because you have that bespoke skill, the spend increases from an operational standpoint. And so the goal here is to simplify the network architecture end-to-end and reduce the number of protocols that you would be running across that multi-domain deployment. And because you make things look very similar across the multi-domain deployment, then it's going to be easy to iterate the designs across that multi-domain architecture. At the end of the day, everything looks and feels the same, so you will be able to stamp it out across the multiple domains. And with that, obviously, this is conducive to automation, where we can enable that service orchestration and the automation on top of the end-to-end environments. But what should be your strategy? A single, consistent end-to-end operational model for service delivery. And there will be no secret that my focus today will be on network overlays, EVPN. And why? Because EVPN provides us with the ability of riding on top of any transport option and offering services. It's open standards, there is no vendor lock-in, and we are able to converge a set of skills across the different domains that we are going to run this upon. The other aspect is it is connectivity agnostic. If we think about the transport options that I mentioned, for example, in the data center, you may operate this with IPv6 in the transport layer. If you are thinking about the WAN, then you will have an MPLS SR deployment. If we are thinking about the branch, maybe you need encryption, and that's where you would be using things like VXLAN, SEC, or IPsec. But EVPN will be able to go on top of all of those transport options and offer services to your tenants. And the goal here is not to lock you into a proprietary architecture and to give you future-proofing, the ability to change the transport at your own pace, and there is no need for a big bang approach. You can do it progressively across the end-to-end deployment. But there is a level of complexity, and the EVPN RFC landscape does look somewhat cumbersome. And if we think about all of the services that it provides, E-line, ELAN, Layer 3 VPN services, maybe multicast delivery in the VPN overlay, or general routing, then there are many RFCs to give us those capabilities. And vendors have to get to the point where they have a solution stack that can easily interoperate with other vendors. That's their challenge. And in order to solve that challenge, that's where the European Advanced Networking Test Center comes in, otherwise known as EANTC. EANTC hosts an annual event over 2 weeks, usually in the beginning of the year, where vendors, for the first time, come together as friendlies rather than competing with each other, with a view of providing that unified architecture and the interoperation between the different vendors. The focus is on the next generation technologies that cover the data center use cases and the service provider use cases. So think about testing that gets done on top of EVPN VXLAN. There is EVPN SR, MPLS. There are SRv6 tests, but also timing and clocking, and also SDN and PSEP. At the end of all of those tests, there is a white paper that gets published, and the results are also announced at the MPLS World Conference. By the way, the name of the conference has just changed. It's now called the Upper Side World Conference in Paris, which is basically happening these days, and the results are going to be available there. A lot of us vendors choose to be there every year, and we look to test our solutions against other vendors to ensure that we have that interoperable deployment. Some other vendors may choose to come every couple of years to ensure that their code releases are going to be compatible. So we spoke about the fact that the goal here is to have a multi-domain architecture. And that multi-domain architecture, if we look at the diagram, consists maybe of data center deployments with that typical leaf-spine fabric, with IPVXLAN as the protocol that provides us with the associated services. If we then look in the diagram towards the core of the network, that's where we have MPLS SR. And then in the branch, maybe you want encryption. So securing the traffic that leaves the branch and reaches into those domains, that's where you would be using VXLAN sec as an option. And what I mentioned is that what it's required is that uniform service layer that allows the end-to-end stitching of services across the different transport options. And EVPN gives us that uniform stitching layer. The key here is that I'm going to leverage different transport options across those domains. Well, I can use EVPN over the top to provide my services regardless of what that transport would be. Now, a centerpiece of the discussion today will also be the EVPN gateways. Remember that I'm switching over between the different transport options. Think of the EVPN gateway as the glue between those different domains, as the point in the network that allows me to translate from one transport option to another. I will talk more about this, so keep that in mind. But why EVPN? Why EVPN for service delivery? Well, first and foremost, it used to be about multiple protocols before. To solve a problem for E-line, ELAN services, for multicast services, I will need to run very different protocols. But with EVPN, the goal here is to have a single BGP address family that would allow us to offer those services in a unified manner. And now I have a repeatable deployment pattern, if you will, consistency across the end-to-end deployment. And consistency obviously enables automation. The other aspect is resiliency. No matter what the domain would be, I will be able to have active-active multi-homing and no single point of failure. And with EVPN, I will be able to offer that in much the same ways. Any encapsulation that comes to the transport options that I was discussing about, an EVPN can ride on top of everything. And then because everything looks and feels the same, then the skill set will be unified end-to-end. So now let me provide a high-level view in terms of the individual domains and their protocol stack. So if I talk about the campus or the data center, most likely you will be deploying, let's say, a leaf-spine architecture, or maybe a close variation to that. Under that leaf-spine architecture, you will likely run IP. Why? Because you don't need advanced control of the bandwidth in those domains. But as you move towards the WAN or the backbone, that level of control is required. And that's where segment routing or traffic engineering comes in to offer us that flexibility in controlling the available capacity. And then finally, in the branch, as I mentioned, you may be using things like VXLAN sec or IPsec to provide you with the associated connectivity options. So I spoke about the fact that we have the multi-domains, right? We have the data center, the campus, the branches, the carrier core. And I spoke about the fact that a centerpiece of our design is going to be the EVPN gateway. And there are two main functions for an EVPN gateway. One, stitch the domains together, but the second aspect is improving scale between the domains or within a given domain. And for a second, I will get you to focus on the diagram on the right-hand side. The use case here is interconnecting intra-domain pods for hierarchical scaling. So imagine that I have a large data center environment where I have multiple devices. In that large data center deployment, I may have multiple leaf-spine fabrics. To interconnect those leaf-spine fabrics, I could use the gateway and think of the gateway as the proxy in between all of those environments. If you will, the gateway hides out the complexities of each and every environment from all of the other environments. It allows us to scale by hiding away what's happening inside a given pod. But the second aspect as part of this is interconnecting the domains, which is on the left-hand side. And on the diagram there, I have two data centers left and right, IPVXLAN from a transport standpoint, and in the middle I have an MPLS service. Well, how do I translate in between those different transport options? It is the EVPN gateway that acts as the stitching point, as the conduit as part of the other domains. And I want to implement this solution using standards, RFC 9014, or the EVPN IPVPN interworking RFC. That gives us the ability of riding on top of multiple encapsulation options, VXLAN, MPLS, segment routing, and it also gives us the hierarchical scaling that I was talking about. And at the end of the day, what do we need to do here? We need to use layer 2 or layer 3 services across that multi-domain deployment, right? And so I need to advertise subnets, or otherwise I need to advertise MAC addresses. In the EVPN world, the subnets are type 5 routes, or the MAC addresses are type 2 routes. And so I spoke to you about the fact that the gateway would give me the ability of hiding out the complexities of each and every environment. And the way to do that at layer 3, the type 5 routes, they are going to be re-advertised by the gateway with the next hop address. Right? So whatever I'm receiving, I'm re-advertising, hiding out the original complexity of the domain. Much the same happening for layer 2 as well, where I'm advertising MAC addresses. In the EVPN world, those are type 2 routes. We are re-originating those with the gateway as the next hop. This is a bit more zoomed in from the previous diagram that I was presenting. And in here, again, I have the data centers left and right, and in the middle, I have the MPLS environment. So what is the EVPN gateway behavior? Well, the gateway sits at the confluence of those environments, and the VTEPs within the data center, let's say, will peer with the gateway, usually using BGP or IBGP. As part of that peering with EVPN, I'm going to leverage EVPN route target imports and exports to basically pull routing information from my domain and then re-advertise it to the remote EVPN gateways that are connecting to other domains. And so when exporting between domains, remember that I'm changing the encapsulation as well. I'm moving from IPv6LAN into MPLS. So I may need to impose a label in the MPLS world to change from one transport option to another. What are the benefits? An end-to-end layer 2 and layer 3 service delivery, regardless of the transport option. And then I'm going to have those hierarchical flood lists that would reduce the churn across the domains, and it would allow me to have bigger scale. All right, I spoke about the end-to-end deployment from a holistic point of view. Let's zoom in into each and every domain right now and uncover the protocol stack and the design patterns. And I'm going to start with the data center and the campus, and maybe I'm committing a bit of a heresy here by talking about both of them as a unit, but hear me out. All modern data centers and campuses require a network overlay. EVPN VXLAN is typically the right choice. And why? For simplicity. I have a physical architecture. If I deploy an overlay on top, I'm going to be able to abstract away the physical architecture and offer services anywhere as part of that deployment. And the other aspect is, why not use it? All modern hardware these days supports EVPN VXLAN. In the data center and the campus, I also have vast amounts of bandwidth to my disposal. So I don't need things like traffic engineering or otherwise fast reroute capabilities, things that I will need in the WAN. Why? I have a leaf-spine fabric, and that leaf-spine fabric could very well be connected at 100 gigabits per second or even higher. VXLAN operates on top of IPv6 if you want to do that, and if you're running out of IPv4 capacity, and if you have exhaustion problems. So from a protocol stack standpoint, this is the RFC framework, and we have the overarching RFC 8365, and that gives us a number of sub-capabilities. EVPN multi-homing for active-active attachment. If you think about the data center, maybe I have servers that need resiliency. EVPN multi-homing would allow me to represent 2 boxes as a single device. Then I have the integrated routing and bridging capability that would allow me to route at the closest point to my workloads. Those would be the Anycast gateways that I can stretch across the fabric, if you will. EVPN OISM would give me layer 2 and layer 3 multicast services. And then finally, the EVPN gateway we spoke about, that's the ability of stitching to other domains or otherwise improving the scale. So from a design standpoint, how does this look like? I have a leaf-spine fabric more often than not. I will be building this at layer 3, and I have options. So SPF, ISIS, BGP as an example. All of them are perfectly valid, but if I'm using BGP in the overlay, well, why not use it in the underlay as well, right? So BGP in the underlay. I will be able to achieve tenant services and network segmentation by leveraging EVPN on top with that route target import and export, creating VRFs that stretch across the multi-domain environment, or within the domain, I should say. And I have the ability of deploying any endpoint anywhere. That's done through the EVPN IRB capabilities, where I have symmetric or asymmetric routing. I'm not going to get into the details, but with symmetric IRB, you can basically have a gateway, an Anycast gateway that's stretched anywhere across the fabric where you need that gateway to be. Therefore, your workloads are going to route at the closest point. And then the final diagram there relates to multi-homing connectivity. All right, so from a evolving trend standpoint within the data center, those are some of the services that we see out there. tenant multicast services. So for example, for media and entertainment workloads or video services, you will be using the EVPN OISAIM framework to give you layer 2 and layer 3 capabilities at the multicast layer. Hierarchical EVPN designs are certainly popular for very large deployments. And then collapsing the MPLS PE by having one leg into the MPLS world, one leg into the IPVXLAN world. That will be your border gateway out of the environment. And then in certain scenarios, you do require encryption. IPsec, VXLAN, VXLAN-sec as an example. All right, so I spent some time describing the protocol stack and the design patterns inside the data center, but what about outside of my data center environment in the carrier core in the WAN? The requirements are changing a bit in this case. Why? Because I don't have the luxury of having a full mesh topology that I used to have in the data center. Typically speaking, you have a partial mesh or maybe ring topologies or ladder topologies. In this case, I do need the ability to control the bandwidth. And MPLS and the various transport control plane available, LDP, SR and RSVP, give us the options of fast reroute and traffic control over the WAN. But SRv6 is emerging and evolves this concept by using the native IPv6 data plane, where we encode a label stack in the data plane, and that would dictate the path across the network, basically. And why segment routing for transport? Let me do a 30 seconds overview of what segment routing does for us, for those that don't know what it's used for. So in segment routing, I usually implement routing at the source, and I do that by implementing a label stack. And that label stack would give me the vectorial path across the network, and it would dictate how I'm going to consume my available infrastructure, right? So I program a label stack on ingress, and that would dictate the entire path across the entire fabric. So starting with that knowledge, the protocol reduction is key with segment routing. IGP is used for segment distribution, label distribution, and removes the need for additional dedicated protocols like LDP or RSVPTE. And because segment routing allows me to program the label stack at the ingress point, then I don't need to have that state across the entire fabric, and therefore it's much more scalable. It gives us the ability for convergence with fast reroute, where I have things like TILFA, allowing 50 milliseconds of convergence in case of failure. And then I have traffic engineering with controller or controller-less solutions. FlexAlgo and dynamic SRT are good options in this case. And because I'm using a segment routing as a unified concept in the WAN, then I can apply incremental skill sets based on what I already know from the MPLS world. So again, I'm kind of talking about the underlay here. What are the segment routing choices? I can have MPLS SR over V4, or I can have MPLS SR over V6. In this case, the SR segment identifier, or seeds, are programmed as an MPLS label, and they are consumed in the data plane to make routing decisions across my fabric. And I'm basically reusing the MPLS IPv4, IPv6 forwarding plane. And because of that, I don't need to have a forklift upgrade across my infrastructure. Finally, when I look towards SRv6, I'm actually doing away completely with MPLS in this case, and I'm programming what are called the SR micro seeds directly into the IPv6 headers, into a new header that's actually called the SR header. And because of that, I actually need new devices that have the capability of interpreting the SR header. So it comes with a bit of a forklift upgrade in this particular case. But SRv6 presents us with a number of interesting options. Because I'm leveraging the IPv6 headers, and within that IPv6 header, I now have an SR header where I'm able to program a label stack that would dictate the path across the network. well, can I not do that directly at the server level? And for example, an interesting use case would be traffic engineering for AI workloads, where I program the label stack directly in the server, and then I'm dictating the path from one GPU to another GPU across my fabric. And why? As you know, job failures in AI deployments are actually a big no-no. It comes with a lot of power consumption, delays, and increased cost. Other options would be 5G and network slicing. We all know about that, or otherwise service chaining. And from a service chaining standpoint, maybe this enables new revenue streams for you as an operator, where I'm able to interject services in the data path dynamically. For example, putting a firewall or any other type of service that would sit in the data path. Okay, so I spoke about the transport in the WAN. Now let's speak about the services that sit on top. And I will create a parallel to the typical ways of implementing E-line, ELAN, IPVPN layer 3 services, or otherwise multicast layer 3 VPN services. And we used to have different protocols and different RFCs that would give us those capabilities. You know, we have LDP or BGP signal pseudowires as an example. We have VPLS, we have IPVPNs, or we have next generation MVPNs for multicast. Very different, they don't look anything like each other. But from an EVPN standpoint, I'm going to be able to leverage that single BGP address family and EVPN control plane for all of those layer 2 and layer 3 capabilities. For pseudowires, I'm going to use EVPN VPWS RFC. For layer 2 VPNs, I'm going to have EVPN layer 2 VPNs RFC 7432. And for IPVPN services, again, EVPN layer 3 VPNs, and finally for multicast, EVPN OISM. So again, the goal of unifying the protocol stack across any of those domains. In summary, what we are looking for is a repeatable network architecture across domains. And the way to achieve that is through protocol and state simplification. We want to keep it simple and consistent. And when it's consistent, it's also conducive towards automation. With that, thank you very much.
Do we have any questions?
Perfect.
No? No questions. Okay, thank you very much.
Thank you very much.
And our final speaker for this session is Alan, who's talking here about free radius.
Thank you. If I can get a little bit of water first. 3 hours of doing the workshop yesterday, followed by yelling at people in the bar. It's a little much. All right, so I'm here to talk about Radius. Radius is the protocol that will never die. Who am I? I'm mostly known as the free radius guy. My background is farming. Don't like sitting on a tractor in 35-degree weather. So I did nuclear physics, which was clearly a smarter thing to do. No money in nuclear physics, so I got into computers. I've been doing Radius since 1998. At this point, I've written most of the Radius standards. I tell people I was late to the Radius game because there were lots of people doing it before me. But the fact that I've stuck around for 25-something years means that everyone else retired. And now I look around and I'm pretty much the senior Radius person, which is a little scary. I have a company behind it, etc. So why should we care about this thing, right? I try and hire people, I interview them, and they're like, I thought Radius was dead. You know, everyone moved to diameter. No, there's good reasons for that. I was there at the start when diameter started being defined. I unsubscribed from the diameter list because I had great confidence that it would go nowhere. I was sort of wrong. It did go places, mainly in the 3G, 4G, 5G space, but diameter is gradually being replaced. So why do we still need radius? I mean, it's 2026, we have better protocols, we have better standards. Why not just use JSON, REST, etc.? And the answer is, it'll never die. It's in too many pieces of networking equipment. So $100 will buy you an AP that has probably a copy of host AP in it. It'll do radius. You can download free radius, you can get it all working. What equipment does diameter? And the answer is you pay $100,000, $200,000 for the diameter equipment. You pay $100,000 or $200,000 for a diameter license. It's not in people's budgets. On top of that, there really are no open source diameter servers. There were two. One was called Open Diameter, one was called Free Diameter. They implemented the protocol, but they missed the minor thing of policies and talking to databases. So they were theoretical and completely useless. On top of that, radius is baked into 802.1x. Broadband, for example, does not use 802.1x, but anyone familiar with EduRoam or Open Roaming knows that's all radius. I found out recently, I didn't know this, that we have one person at Microsoft to thank for that. Everyone else wanted to use diameter, the IEEE, and the guy at Microsoft said, Microsoft doesn't have a diameter server, so we have to use radius. In hindsight, I think that was a good decision. So we're trying to fix it. Has anyone ever had problems with the radius protocol? It's a bit of a disaster. So in 2007, I wrote RFC 5080, which identified a whole bunch of issues with the radius protocol, suggested fixes, didn't mandate them. Since then, we've added a lot more to the IETF wiki that we maintain on GitHub, and there are dozens of issues with implementations. In the end, these are things that cost all of you money, right? You buy equipment, it may or may not work, it may or may not do what you want, you may have to have workarounds for things the equipment does or does not do. One of my favorite phrases I hear from vendors when I try and argue with them is that the standards allow them to do a particular piece of behavior. That's almost always not true. Most of the radius standards were written in the late 90s, and they are simply silent on a wide range of topics. I don't know if anyone's run into this particular issue, but we did. Nothing in the accounting standards says that the data has to have anything to do with reality, and it doesn't have anything to do with authentication. So there is equipment which says that user Bob logs in and all the accounting data is for user Doug. Why? Well, we're allowed to do that. Makes absolutely no sense. It costs people money. So blast radius, esoteric security issue, that was fun. The researchers involved had done some improvements on MD5 cracking. They discovered an issue, they called up the IETF. The head of the IETF went, I don't know, it's radius, talk to Alan. They called me, and I was like, okay, I don't know, whatever. They explained a little bit, and when they explained the issue, I went, oh yeah, that. And I went back and double-checked the mailing list archives. I had been complaining about that since November 1998. Now, despite having a background in nuclear physics, I'm not a super math guy. I I did not do any of the math to prove that the exploit was true, but I could point at it and see it was broken. Even RSC 5080 suggested ways to fix it. The problem is basically that some packets were not signed. For a security protocol, that seems like a fairly dumb thing to do. The feedback I got in 97, 98 was too bad. RFC 5080 said you should really sign the packets. To my knowledge, there was only one implementation that ever did that. And then as we came up with the fixes, it was good for about 6 months of work where I defined the fixes in conjunction with the cryptographers. And the critical thing was we had to make sure that we didn't break anyone's networks, right? Because the worst thing that can happen is you have a security fix and you have a flag day and your whole network goes down, you implement the patches, you hope it works, and you bring it back up again. So there was a lot of work that went into that, a lot of arguing with vendors as to what was the good approach and whether or not the approach that me and other people were recommending was the actual correct one. The good news is we basically pushed them all into submission. They all did the right thing, and the outcome of that is we discovered that some equipment did not support some of the radius standards that were 25 years old, because nobody cares about radius. So, in the interest of moving forward, we had a radius conference in Tampere, Finland last year. I was there, the Radiator people were there, RadSec Proxy was there. Cisco people couldn't attend, the Nokia people weren't there. HP has ClearPass, they attended virtually. What we did was we sat around with a bunch of operators. This included the key EduRoam people and other operators, open roaming people, and just went, let's sit down and brainstorm. What's wrong? What problems are you running into? And this is one reason I'm here today. It's not just to talk at you, it's to discover what problems you have and see what we can do to fix the standards. So we're having another instance of that held in conjunction with TNC, which just happens to be in Helsinki. So for some reason, Finland is very exciting for the radius space. What we did is we identified a few key changes which were costing people money. Some is good practices, so things like load balancing, especially for 802.1x. If you look at RFC 2865, which defines radius, it has this wonderful phrase that proxying and load balancing is a subject of future research. That was published in 1997, if I remember correctly, and pretty much nothing has happened since then. So again, this is one reason why we're here, trying to discover what works for you, and the outcome of some of this was recommendations. There's also a new packet being defined. Radius has this wonderful property where some packets are silently discarded, and from a network protocol design, this is a disaster. You have a known piece of equipment, which is trusted. It sends packets to a known server, which is trusted, and the server goes, nah, I don't care. Throws it away and doesn't respond. This causes stability problems in people's networks and costs people money. Another issue is reject. We've talked to people where 99% of the radius traffic is rejects, right? This is a massive load. In EduRoam, 30 to 40% of the traffic is rejects, because once you have a profile on your phone, it goes to your next phone and your next phone and your next phone. Every time you walk by a campus, even though you've been out of university for 15 years, your phone tries to connect. So in the reject case, What we're proposing is a way to cache rejects. Basically, the home server, IDP, whatever, can send a response back going, you know what? This person hasn't had an account for 5 years. Please don't ask me about them again for the next hour. And it's a small enough time frame to get rid of most of the bad traffic, and also small enough that what happens is it doesn't affect the user experience. Because the last thing you want to do is block a good user or a known user for a day. People in other standards bodies are finding this useful for things like legal compliance. People are not allowed access to certain networks because they haven't signed an acceptable use policy, or they're too young. So you reject them, but their account's valid, so they try again, they try again, they try again. And it's much better to go, you know what, while you're visiting that network, you do not have permission to access it. And then there's a best current practices document, so there's 4 or 5 new standards that are coming out. For anyone using RADSEC, you'll be happy to know that that is being standardized. The original name was Radius/TLS. Everyone's decided that the market has spoken. It's now called RADSEC. There's another document which is a review of Radius security, which discusses what has happened over the years and the good and bad parts of Radius. And then there's another standards one which is deprecating insecure practices, and this will affect broadband people. This will affect vendors who are selling broadband equipment. And then another one that's coming up is radius level traceroute. This is less useful for broadband, but for people like eduroam, open roaming, it's very useful. You send a packet out, and rather than getting no response, or rather than getting an unknown response, you can get an entire trace route of how that packet went through the network. So, some technical details for people who care about radius. Protocol error is basically a canonical NAC packet. Thank you for sending me that packet. I don't know what to do with it. You do something else. It's your responsibility. What this means is when you have a chain of proxies, right now, when the final server discards the packet, you have all this data which is live across this chain of proxies, and they have to sit on it until they all time out, versus replying and going, nope, 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 that gets cleaned up all the way back up the proxy chain. You lower the load on proxies, you increase network stability. Everyone likes network stability. In the last IETF in Montreal, everyone sat down and implemented this. So it's now at least in alpha, in Radiator, in RADSEC proxy, and in FreeRadius. We have confirmation from Cisco that they will be implementing it. They have agreed to do that. And if any other vendors need help doing this, please reach out to me. I'm more than happy to help. So this means that, just another slide on protocol error. Signaling errors early is much, much better than having people wait for timeouts. It's just a disaster. It's just good network design. Reject cache, the reject cache should help substantially. I know I've talked to broadband customers who have equipment connected up through various layers of providers that they can't convince the customer to disconnect it. They can't convince the other providers to disconnect it, and 99% of their packets are rejects. And this is a big load on the network. It's even worse when you have multiple chains of proxies. One of the things that the eduroam people ran into was that they saw badly behaving supplicants sending thousands of packets a second. And this just overwhelms the proxy chain, because you could have people doing this at multiple sites and take the entire eduroam infrastructure down. What this reject cache allows you to do is either proxies or BNGs, edge equipment, whatever, you get the reject, and the reject says, please shut up about this user, this MAC address for the next period of time. And when the equipment complies with that, all that traffic goes away and your load goes down. This is fantastic. So technical implementation, we want it to be secure. You don't want someone like me who has good intentions, but I maybe do something at accident to block someone else's users. So the design has some technical details where you can only block your own users and you can't affect other people. So the result is load on the systems goes down enormously. Best practices. There's a lot of content in this document. It's basically the summary of the issues and fixes wiki, where every time myself or someone else in the IETF runs into an issue with inventive behavior, we put something in the wiki. The problem is there's a lot of common practices which people engage in, which make sense. Not everyone follows those practices, and you don't know whether a particular piece of equipment follows the best practices. So the idea here is to codify all that, write down the experience of everyone in this room as to what should and should not happen, so that when you go out and buy vendor equipment, you know it follows the practices that you expect and the practices that the industry expects. And if you have questions, reach out to me. I'm more than happy to help. There's a Radius security document, the history. Radius UDP is being deprecated. It is not secure. It cannot be secured. Everyone will be moving to TLS or DTLS. Interestingly enough, there was an attack on MS Chap about 17 years ago. No one thought to deprecate it then. Fine, we're doing it now. Turns out, I discovered the other week, no one had done an analysis of chat password. So I did some back of the envelope calculations and it was pretty much the same as MS Chap. If you are sending MS Chap or Chap across the network, it takes a laptop and a couple of milliseconds to convert that data into the user's password. If you are sending them across the internet, those users' passwords have been compromised, full stop. Traceroute. This is perhaps less useful for a lot of the broadband community, but still can be useful depending on your layers of proxies. It's most useful for things like eduroam, where you have multiple chains of proxies. How do I get to example.com? Which proxies does it go through? Are those proxies up? How slow are they? Right now, you have no idea. And when there's a failure, the official answer is often telephone the admins of the other servers. Now, this is not a scalable solution. So some of the questions here is, what information would be useful in the traceroute? So to close up, I'm here not just to lecture you about what's coming up next, but also to ask you for your help. What problems do you see in Radius, and what do you want fixed, and what do we need to put in the documents to fix them? So Radius will get better. It'll never go away, but the hope is to make your lives easier. Thank you, everyone. We have a short period of time for questions. For my workshop yesterday, I did send the slides to the organizers so they can be shared. There's not a lot of notes on them, so sometimes the context isn't always there. But questions? Yes.
Have you ever heard of a Radius issue where if a vendor's network equipment and the system that manages the equipment, they use the same vendor ID by default because it's from the same vendor,
Yeah.
and the Radius wouldn't work properly? So you have to manually change one of the system to use a different vendor ID. for it to work.
So you mean they have different attributes under the same vendor ID?
Well, I don't know the exact attributes they use, but yeah, we've got, say, ISAMs from the vendor and the system that manages that ISAM. In their notes, it says you have to manually update the vendor ID in one of them.
Yeah, there isn't a lot you can do about that, again, because the RFCs don't say you're not allowed to do that. And often, I mean, companies are big, right? Not every department talks to every other department, and these things happen. So this is the kind of thing that we hope to be able to write down in the documents and recommend what people do, so that your lives will get easier. Yeah.
And is there anywhere we can check the list of vendor IDs in the Radius system? Because when they try to update the vendor ID, I just pick a random number. I think that's not in use.
Yes. There is no global registry of Radius dictionaries. The closest thing is the Free Radius GitHub. If you want to look at vendor IDs, they're actually called private enterprise numbers, and IANA manages those. So if you look up, that's the Internet Assigned Number Authority. And if you want one, literally you email them and ask, and they will get you a number that's unique to you.
Thank you.
Yeah. Any other questions? Okay. I think that's good.
No more questions. Thank you very much, Alan.
Thank you.
Okay, so that's it for the first session. We've got a break now. We're back at 11 o'clock. So if you missed out on coffee earlier, now's your chance.
Okay, thank you everyone. Welcome back. Hope you managed to get some coffee from our wonderful coffee sponsor. First up in this session, we've got Matt Inger. Matt's from Australia in Melbourne, but Matt's actually been really involved in the New Zealand space over the last few years as a committee member for NZIX, and he's attended the last few NZNOGs. And today he's going to be talking about something you don't normally hear in the same sentence, which is scalable MikroTik CGNAT. Anyway, thank you, Matt. Come on up and welcome.
Thanks, Dave. Yes, scalable MikroTik CGNAT solutions. For my sins, I actually use this stuff. So I started a business. I thought it'd be a really good idea to start a residential ISP. And of course, I was funding it myself. So you look for the cheapest hardware you can that's going to get away with. And this is what we did. And this has been a continuous journey. So I'm going to give you a bit of introduction to who we are, what we're trying to solve, and we're going to actually make it happen. So I've actually got configuration here. So if any of you are interested in actually deploying this, you can take my slides and off you go. So who am I? I'm a self-taught network engineer. If it is a way to do it wrong, I've probably done it. I am owner of an internet provider in Australia called LeapTel. We're about 76,000 subscribers now, so we're no longer small, but we are still having fun and growing with MikroTik. But I'm also very heavily involved in peering. Dave mentioned NZIX. I'm also chair of the Internet Association of Australia, so we do the peering New South Wales IX, which I know a lot of you do join us. So good to see you there. And yeah, I wrote this slide a little while ago. It's 76,000 last week and about 300, 350 gig transit nationally. So we're moving packets. Other reason I'm here in New Zealand is I know some of you buy services in Australia. Come talk to us if you're looking for any of those services. We've actually got some really cool API stuff going now, and you can actually talk to NBN in Australia and pretend that we don't even exist, which can really solve some of your issues and get things fixed quickly. So feel free to come talk to us. So what are we trying to solve? Well, I don't know about you guys, but Akamai may not want me to use CGNAT, but I don't have a choice. I'm a small provider. Lucky I got a /22 originally allocated to me. And from there, I've had to pinch, steal, pay for IPv4. So I'm kind of stuck. So I need a solution. And while the price of IPv4 is actually getting cheaper at the moment, it's still an expensive resource. I wanted just to use IPv6. It's 30% uptake I saw on the Akamai slide in Australia. It's still a real pain. Adoption in Australia is pretty poor. Some of the really big guys have done it. It helps that they're using their own routers. But the smaller scale or the challenger brands, it's still very low uptake. Many businesses in Australia aren't even considering it, I suspect, similar in New Zealand. And consumers aren't even convinced to do it either. So our IPv6 experience, we are dual stack. We offer a /64 on the WAN port and a PD allocation of /48. We're a largely IPOE network. Tried doing IPv6 on Router OS 6 and gave up. But we now are Juniper BNG shop and it actually is working pretty well. We did have some challenges though. IPv6 to me is a protocol designed by a whole lot of academics. They came up with 3 different ways to do it. All 3 ways got implemented, none of them work. So it's a real pain and a challenge. And auto configuration just does not auto configure because nobody can agree on what they're trying to configure. So introducing CGNAT. I know we're a technical audience, so I won't spend a lot of time here, but CGNAT is basically NAT on a large scale. What we're trying to do is do it in a way that scales, but do it in a way that law enforcement is also going to be happy because they're going to send us requests. They want to know who's been doing those naughty things. So what we're trying to do, cost effective. I have running this on a credit card. Law enforcement, keep them happy so they don't shut me down. And learn some of the things that we have from commercial offerings to try and put them into these solutions. There's a really good presentation that Aussie Broadband did at NZNOG quite a few years ago when they employed CGNAT and their logging, and they said it was like 25 gig of logs per day when they were logging every single interaction at the time. Our solution, the only logging we're doing is radius packets. Yes, radius isn't dead, but we're just keeping track of the IP address and we're allocating on radius there 100.64 IP, and then we could use a spreadsheet to reverse engineer. Logs really simple. We're doing 250 ports per customer, and I'll explain how we get away with that on a MikroTik, and it just works. So LeapTel, we were using this. We still are using it in our smaller locations, and there's a photo of our Sydney POP at the time. You can see there lots of MikroTik, not much of it there anymore. 250 ports, does it work? Yes, it does. And the reason it works on MikroTik is that the MikroTik keeps track of both the source and destination IP and port and will reuse them. So we can map 2 people on the same source port because they're going to 2 different destinations and reshare the port around, and it works. One of our staff who happens to be here, I won't name him because he'll be embarrassed, accidentally set his router at home to be 1 port and he didn't notice for a couple of weeks. So it really does scale. The current design we had the BNG directly connected by a cable to the CGNAT on 1 port, and then the CGNAT was out to the internet. Works really well until the device fails, but it worked. So what did we use? MikroTik CCR 2216. These boxes are about 5,000 Australian dollars. They've got 200 gig ports, a whole lot of 25 gig ports that I never use. 16 ARM CPUs and 16 gig of RAM. But what can they do? They can do 42 plus gig. And this box just worked. I think when we did this, it was because one of the other boxes did fail and we had to put 2 through the 1. It just purred along and kept going. So what were the limiting factors on the MikroTiks? When we had it doing 42 gig, 75% CPU usage, which is dangerous levels on a MikroTik because that's when they start to do funny things and they reboot on you. Connection tracking is actually the limiting factor on these. It's not necessarily the hardware diagram shows the lanes to the CPU. There's a limit of just over 1 million entries in there. You read the MikroTik wiki, it does say that it is dynamically scales, but it actually dynamically scales to that limit. I did contact MikroTik and say, hey, could you please consider increasing it? So far they haven't. So you will find that you start to hit a limit on them and that's about it. But yeah, the 4 times 25 gig pass to the CPU didn't help. The other thing that's not in these solutions, which is where the commercial solutions are really, really good, is the dynamic port application. So because we do this as a fixed allocation on the device, we have thousands of rules on the firewall. It does mean that you have to pre-configure everything. So it's not quite as neat, and it does mean that you have to think about it a bit more, but it does work. LeakTel future design. Well, this is actually our current design now in Perth and Adelaide. We're using switches in the middle, and we're actually basically setting up these as paired units. So 2 BNGs, 2 CGNAT appliances, and if one CGNAT fails, the other one will take over the load for it. We just keep pairing them up and scaling them horizontally. Works really well. So how do we make this happen? The design I'm going to talk about today is using VRRP towards the BNG. Right at the end, I'm going to talk about what we did in the end, because we actually switched this over to BGP. But for my lab, I did it with VRRP, and it actually works really, really well. We're doing BGP towards the layer 3 switch for the internet side, and we're using AS prepends to control which one is primary, which one is secondary. We're doing static allocations. We're actually using the script found on the MikroTik wiki, and just use it, it works. The limitations on this design is it assumes that one box is either fully online or fully offline. If you decide to set this up and you use one port towards the BNG and one port towards your layer 3 or internet side, and one port goes down, you may not quite get consistency because it loses half the connections and the MikroTik doesn't adapt. So it needs to be either fully on or fully off. So this was my test rig. Good thing about MikroTik, pretty much any MikroTik will do for the testing purposes. These are just some 3316s I found and a Arista 7280 at the bottom. And they were all running 7.19.3. That's my configuration. I've got all the IPs there. So two BNGs, in this case we just had the one. 2 CGNAT boxes, which we did do the configuration on, pointing towards the layer 3 switch. So configuring the MikroTik network. So the idea of this is to try and do it as much of a template as possible. So as you can see, the differences between the two is very minor. On the first one, we're creating a VLAN interface for the internet and a VLAN interface towards the BNG, which is a bit further on. Geez, I'm getting old with my glasses. Yeah, we're assigning IP addresses, and as you can see, thank you, we are actually assigning 2 different VRRP IP addresses because we're running 2 VRRP sessions, one for BNG1, so it's primary, and one for VRRP towards BNG2 for it to be primary. So that way, if one fails, it switches over, controls which one's primary and secondary across it. And yeah, VRRP 2 configurations, that's why the IDs are different, but you can see they're just reversing numbers between the two. Internet side, this is the VLAN I was trying to find. Very simple, nothing exciting. Intentionally didn't use routing protocols on this component for the IP default route because I like to try and keep things really simple, really fast, because everyone knows MikroTiks reboot quickly. The less you make them do on a reboot, the better. Pools. So we use a bridge interface and assign the IP addresses that we want the MikroTik to actually hold to push towards the public side. So on our examples here, we're using 14 IP addresses per MikroTik, 7 of which are going to be used for BNG1, 7 are going to be used for BNG2. In order for this to work, we have to put all the IP addresses on both devices, but because we're using the AS prepend on BGP, the external side knows which way to go. Internet side, put your hand up if you've done BGP on a MikroTik version 7. Oh, it's growing. I actually had to learn it when I did this one because I was a version 6 person. So, create 2 firewall access lists. As you can see, CGN1 is for the IPs assigned to the public side of CGNAT1. CGN2 is the public IPs to CGNAT2. Apply that to both units. Adjust connection tracking. This one is so that you can scale your unit. The default configuration on the MikroTik is the session will last 24 hours, and you'll be surprised how many sessions don't close off. So by reducing it down to about 31 minutes, it means that your sessions will clear pretty quickly. We found that this scales quite well. The only catch is that if you leave your SSH session open, unless it's doing keeper lives, it will drop it off after 31 minutes. Filter rules. So this is how we do the AS prepends. So on Router OS 7, you create the filter rule, and we specify that if it is for CGN1 on CGN1, just accept the route. If it's in CGN2, we prepend 1, and on the other unit, we just reverse it. Really, really simple. After you've got the filter rule, you create the BGP template. So as you can see here, we're just using an internal AS number because it's only between our devices. You could choose to use your internal AS if you want to. But we can see that we're using the actual filter rules on there. So where is it? Yeah, you got output chain dash filter. So output.filter dash chain equals eBGP. And that's how we apply that filter to make it actually work. Establish the BGP connection. This is just registering your upstream hosts. So very simple config, IP address of the box upstream, tell it the local IP address, tell it to redistribute connected routes so that it is trying to pass everything out, and then the filter is what actually specifies, so it does the actual, prepending. Yep. So what does it look like? On my Arista, I don't know if you can make that out, but you can see that every single public IP address is listed twice. One's got more of an AS prepend than the other. Static port allocation setup. So we need to apply the same rules on both devices. In production, we're doing 32 IP addresses per unit, which means if we're doing failing over doing 64, you do need to be patient, especially when you're applying the second set of 32 IPs, because the memory is getting a bit built up and the way it adds it is a bit slow, but it's once off, it works. So we need to build up a table. I don't know how many of you guys use Excel for everything, but I certainly do, especially before NetBox came around. But we create a table. So columns, BNG IP, public IP address, start port, finish port, and basically we build the IP address out. The reason we do this is that we need to allocate from port 2000 onwards, and I got a little lazy here. I didn't go back to 1024, I chose 2000. And the reason I do this is that when I receive a law enforcement request, it's really easy to figure out which block it's on or which line, whereas if I'm trying to use 256K or two boundaries, it gets really hard for my brain to try and read it in Excel. But it works really, really well. Do this. So you put all of them in. You then take the MikroTik script, which is this one. You can find it on the wiki. I'm not going to try and read it to you, but all it does is loop through and add the firewall rules into place. And then I basically filter the MikroTik, the output, so that I only show port 2000s, and then I use the concat function to create the commands to run to actually generate the firewall rules. And then you do this. There we go. So I've gone to my Excel sheet that you can't see, and I've just copied that previous column on, and I literally pasting now the script from MikroTik, and now I'm going to paste from Excel. You can see it takes a little bit of time. But it's done. That's it. Almost. This will only set up TCP and UDP. If you want to do other protocols, ICMP, IPsec, you'll need to add some rules in for those. They don't allow tracking back for law enforcement, but it at least makes them work. And as we know, a lot of customer routers these days will do a ping test to confirm connectivity. If you don't put this in and have it working, you will be getting a lot of calls to your call center. So another thing to consider is you need to enable fast track. This is a paste from the MikroTik wiki from a different router, but it does show how much of a difference on CPU with or without fast track it happens. So it's 2 rules to add. copy paste, done, and it makes a massive difference. So, how well does this work? Well, MikroTik's reboot, what's it going to do? There's me running a ping from my pretend BNG out to the internet through this, VRRP running. I had VRRP set to timeout every second and had needed 3 seconds or 3 timeouts to actually cause a failover. So the unit should detect this changeover or the problem within 3 seconds. And as you can see there, it very quickly switched over. What does BGP look like when that happens? Table shrinks. So one thing that the commercial vendors like to push is having CGNAT, having 2 appliances, synchronizing the connection tables, and basically if one unit fails, the other one's going to pick it up straight away. MikroTik doesn't have that quite working, although the VRRP does have an option now to do connection table synchronization. Haven't tried it, but my question was, does it honestly matter? Here's a production test proving it doesn't. This was one of our units in Melbourne, and as you can see, it went down for about 60 seconds. As soon as it came back up again, the traffic pretty much just resumed. And this is, I think, largely due to the fact that Quick just automatically, basically after 30 seconds, will reconnect in and reset its everything. So a lot of stuff just keeps going. So don't need all the fancy features, it just works. Some real-world improvements that we have made to this. I mentioned at the start, we've moved from doing VRRP to doing BGP on the other side as well. So we're basically pairing these off. BNG1, BNG2 has a pair of MikroTiks, BNG3 and 4 have its own pair of MikroTiks. We're doing BGP to the different MikroTiks together, to the different pairs together, cross-connecting them, and we just handle all the signaling on BGP. This is working in production really well, and I rebooted one in WA a couple of months ago and the traffic just switched. Customers didn't even notice it. In fact, I didn't even realise it had switched when I did it. I was expecting an outage, it didn't happen. So you can change this to BGP, just change the rules that I did in the previous component, and it's really easy and it works really, really well. So conclusions. Very cheap solution, $5,000 a box. Now I was using these MikroTiks for BNG originally, so I had extras left over. So I've been able to repurpose them to be used for MikroTik CGNAT, and it's been a real changer for us because we don't have to purchase new gear. They have a very quick cutover time and they work very well. My challenges are scaling limits. We're basically hitting 42, 50 gig. That's about the limit these boxes are going to do. The static mapping is not very efficient use of IP address space, and it will randomly reboot, but it comes back quickly. Thank you.
Any questions from the audience?
John Brewer here, just with a question. 20-some-year user of MikroTik here. Have you thought about using x86 boxes instead of MikroTik hardware itself?
I have actually looked at it. Part of the thing was for us, the price tag of $5,000 was pretty low that it didn't matter to us. And I still think I had the same scaling limit on connection tracking tables, that it wasn't worth the extra investment for us to do it. Although you could then go, I guess, multiple VMs on the same box and start scaling horizontally on the same hardware. But I did quite like the idea of just having the box and being able to pull them in and out, and it was just there.
Yeah, so similar questions to John. I've done quite a lot of work with containerized CGNAT scaling at scale with x86. So you've got about a 60 gigabit, 60,000 connections limit on any silicon. That's just kind of your hard limit through fast path, slow path, whatever you would call it. The other question I had was, have you looked at using something like FRR in place of the BGP routers on the MikroTiks for doing like BFD? Failure between different instances.
We didn't do anything with BFD, because I know MikroTik does support BFD on these. I know it certainly could be turned on, it wouldn't be hard. yeah, it dropped out so quickly that it probably didn't really make much difference to us.
Might do a couple of questions in one. How did you get to the 31-minute timeout? It seems a very specific number, like 1 minute after 30. Is there something else that's 30 minutes that you need to be longer?
Earlier versions of MikroTik had a default setting for the UDP timeout set to, I think it was several hours, no, less than 30 minutes. And what was happening is that Quick pointed to Cloudflare was giving me massive headaches because the sessions would reset, but Cloudflare was not expecting it to have reset, and actual connections would freeze. That's what I saw.
So just 31 minutes is the perfect
31
number to
minutes resolved it for me, and it worked much happy. And because Whirlpool was behind Cloudflare, I don't know how many of you in Australia know about Whirlpool, it made those Whirlpool users very happy, and they got off my back. So 31 minutes stuck in my head.
And did you get any customers using random protocols that you had to then enable specific rules for? You just dealt with most of them like ICMP, GRE, all of that?
Yeah, ICMP, GRE, there's a couple of IPsec protocols I enable by default. They're the only ones I have done. Because our customers can log into our portal and opt out of CGNAT themselves, I think those ones using anything else probably just went and opted out.
Cool. Any other questions in the room?
Well, I'm around all conference, and I have socks if anyone wants any.
Thank you, Matt.
Thank you.
So our next speaker, he's been to, I'd imagine, 20 plus NZNOGs. He's probably spoken here 20 times or so. He always gets really great ratings in our survey. So welcome back, Jeff Houston, talking about the evolution of TCP transport protocols.
Hi, good morning. It's a pleasure to be here, as always. I'm going to move away from deployment and start to talk about technology. You know, you're all here because of a fundamental shift in the way we built networks. In the telephone world, networking and technology was hideously expensive. You could only afford one of things. And so what you did is you concentrate all of the investment, all of the technology, all of the know-how into this single artifact, the switching network, and surround it with really, really dumb devices, speakers and microphones. And so all the investment's in the middle, all the money's in the middle. The telephone company is really important. Most countries could only afford one. Now, the computing industry came along, and across the 1950s, 60s and 70s, Moore's Law did its inevitable thing. Electronics became fundamentally cheap. These days, you couldn't say that processing and memory is expensive unless you're competing with the AI builders to get some on the market. But basically, we're living in a world of phenomenal abundance. And the change in networking was, I could put really smart devices on the edge. Really smart devices. So I didn't need much from the network. The network could be built out of barbed wire, or as some folk found, carrier pigeons. And as long as there's enough intelligence at the edge, you can sort of paper over the network stupidities. So we started building really cheap networks and surrounding it with really expensive, well, they weren't expensive, but really capable end devices. And so that's the reason behind why we're all here, that we actually build really cheap, quite shitty networks. Sorry, Matthew, but you know, this is our business, and we don't charge users very much. Compared to the old telephone bills, this stuff is dirt cheap because you're doing most of the work yourself with your own devices. Now, inside all of that big change, I think there were two fundamental things that were actually world-shattering for our world. And the first one was actually the transport protocol. Datagram packets are easy, everyone was doing it. But TCP was fundamentally interesting. This whole idea that I can adapt the endpoints to actually accommodate the available bandwidth in the network was shattering. And I'm going to talk about that. The other one which is amazing is Quick, more recently. I don't know where your 31 minutes came from, Matthew. It's meant to happen within 2 round trip times. So something is really, really broken. You or Cloudflare, I can't help. But we're going to talk about TCP. And TCP is one of these issues around evolution. Tip the hat to Charles Darwin and Wallace, who found, 160 odd years ago, that biological life forms actually adapt and change. Oddly enough, our technology is constantly adapting and changing in the same way. And what we're riding through is the last few years of Moore's law. I don't think it's going to last much longer. Physics gets in the way. And for a long time, speed was something that we could double every few years. Speed in your processor, speed in your fibre. And the issue was, with better silicon, with more gates on your actual detector chips, you can pump through an enormous amount of signal. You can do huge amounts of modulation and recover and get the signal back out. So megabit fibre, gigabit fibre, terabit fibre. And then things start to get weird, because although we can make the fibre go faster, it's really hard to get TCP to go faster. Really hard. And I want to talk about why we're getting this issue around trying to make these flow control protocols, TCP, how to make them go faster. Now, for countries like you and I in Australia and you here in New Zealand, even though most of your content comes from data centres, you still have the occasional weird person who wants to pull terabytes of data from somewhere else a long way away. And often they'll complain that the speeds are absolutely crap, and they're right. And, partially it is pick the right protocol and you'll probably get there, but use the right network and you will really get there. And the real question is, what's going on? Why does it mean that the choice of the network and the choice of the transport protocol is actually really, really important? And if you want to get up to terabit speeds in TCP, you've really got to think about how the flow control protocol actually works to do that. So TCP, it's the heart of the internet right now. Even Quick, if you pull it apart, is just TCP in encrypted UDP. It's still the same old problem. And it's quite an amazing protocol because it's actually a flow pressure protocol. Every single TCP stream is exerting pressure on all the other TCP streams that are inhabiting in the wire. Just a certain amount of elbow room. If any session becomes too aggressive, they take over, everyone else goes flop, and people complain. If they exert no pressure, they die. So it's a bit like driving a car on a busy road. You need to keep up with everyone else in order to keep going forward. Go too slow and you've got problems, go too fast and you will crash. And so you're trying to be efficient, use the network, but fair, don't use too much. So that's the kind of what you're trying to do in TCP. And all of this is a flow control protocol. So it relies on feedback. TCP is an ACK-based protocol. The way it works is I send you some data, you send me an ACK. That ACK means a packet has left the network. If I put in the same amount of data as I get ACKs, then I'm putting constant pressure on the network, because every time a packet leaves the network, ACK, I put in another packet. Now, what if I put in 1.5 packets for every ACK? I'm going to radically lift my transmission rate because I'm upping what I send into the network very, very aggressively. If I put in 0.8 of a data packet for every ACK, I'm going to slow down, again, quite aggressively. So all of this is based around how do you process the feedback and how do you react. So a fair protocol kind of keeps pace with the ACKs. But what if I've got a huge amount of bandwidth? Well, I'm not going to use it unless I gently push forward. So what we have in TCP is the second part of this, rate adaptation, to try and make your sessions go faster as you need them to go faster, right? So the way we do this, all of you should have seen the sawtooth. Anyone done networking? You must have. I'll just assume you have. So what you do is you linearly increase the amount of pressure on the network. So I know how long it takes for a packet to get to you and back to me. That time interval, I will increase the amount of data by 1 packet for each round trip time. And what you find is that sawtooth sort of curve that for every round trip time, I'm going a little bit faster, a little bit faster, a little bit faster. Now, you try doing that on a road, a little bit faster, a little bit faster, a bad thing will happen sooner or later. It just will, we know this. You try doing it in a network, a bad thing will happen sooner or later. What will happen? Well, if you think about the way you build networks, you have transmission elements and you have routers. And in that router is a queue. If I go faster than the wire, than the transmission, I'll start to fill up your queues and fill them up and fill them up. And what happens when the queue gets full? The next packet arrives, sucks to be the packet. Bang, off it goes. These protocols are loss sensitive. Loss says, I've not only gone faster than the wire, I've gone faster than the wire plus the queues. And at that point, you back off. The first thing you do is take a deep breath for about 1 round trip time. Why? To let the queues drain, hopefully. And then you start again at a rate that is close to the wire, or so you think. You go at half the speed you were going when you had loss. So that's that classic sawtooth. How well does that work? Not very. How can we make it better? How can we change that algorithm to kind of push a little harder at the network and not be full speed, half speed all the time? What we want to be is no less aggressive, and with a little bit of luck, slightly more aggressive than everyone else, because this is evolution. The mammals win. The reptiles, I'm sorry, they're just losers in all this. So you're not allowed to destroy the network, but you are allowed to take advantage of the reptiles out there and go a bit faster than them. The other thing about this now is that the original assumptions about networking are now all wrong. The most dominant medium in the market are these things. And radio is crap. Radio is noisy, radio has reflections, people keep on moving, damn them. The round trip time is constantly variant. And so radio is a nightmare. 1% packet loss is pretty good for radio. 10% is getting to be hard. On a wire, 10% is a disaster. So radio is tough. If you thought radio is tough, SpaceX, that Starlink service, is a nightmare. Never seen anything worse. If you tried to build a really crappy transmission system, you couldn't do as good as Starlink in building crap. It's brilliant. It runs at 300 megabits per second. It has jitter like you've never seen. It has packet loss, non-congestion packet loss that occurs regularly and catastrophically. But somehow TCP has to work. So how do you do this? Well, this is the magic of trying to make transmission control protocols actually work. I've also got to make it work over your terabit links as much as your kilobit links if I can. And these days, you're not content with building a wire, you build lots of wires. And I'm meant to equally load across all of that. The other problem that I have these days is the traditional Netflix pulse. A lot of video streamers work on high watermark, low watermark. Your playback buffer gets low. I shovel you data as fast as I can to get your playback buffer to high, and then I go quiet and wait for you to go low. So you get thump, 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 which is about the worst possible thing you can do to a network. So all of these are challenges in networking. How did we react? Well, Reno doesn't really work. That algorithm takes forever to ramp up speed because it's linear. You kind of go, how can I go faster? Well, you go back to the mathematicians and go, well, what you need is a polynomial curve. X to the power 3 is a really good curve. And what you try and do is accelerate quickly to the point where you think you're just at that sweet spot, and then slow down a bit around there and probe around that area where you think you're occupying a fair share. And if all of a sudden everyone else goes away, woohoo, put your foot flat on the accelerator and go faster to try and find the new upper limit. Almost everyone on the server world runs cubic because you all run Linux boxes, apart from you dinosaurs running Windows. sucko. And cubic is what comes shipped by default in Linux, so that's what most of you are running. The queue behavior is actually really quite weird. The queue behavior starts to occupy the queue and just sort of sort around that area of maximal loss. So in terms of delay, cubic is actually really bad. It keeps the queues quite full and just oscillates to the point of queue drop. And you sit there and go, well, reacts really quickly to available capacity, that's great. Extends to sort of fit in this period of more traffic equals more queuing, not so good. Works really well on terabit pipes and even gigabit pipes and rapidly scales up, that's good. But remember that whole thing about buffer bloat? It bloats buffers. If you've got network queues, and no matter how big you are, cubic will actually fill them because cubic is trying to find the point of loss, and loss is when your queues are full. What do you want to do? Well, we've experimented with a whole bunch of TCP flow control protocols. Very few of these are in the mainstream. Very, very few. A lot of it's just academics searching for papers, and good on them. You've got to explore every avenue. That's the job. But one of them was fundamentally interesting because what you're trying to do is fill the wire, not the queue. So in essence, you're searching for the wrong thing. If I have buffers that are too big, and most of you do, most of you have bought for your routers from the vendors that go, you need as much buffer space for the bandwidth product of the link you're driving, which sells more high-speed memory, and that's great, but it's way too much memory. What actually happens when you've got too much memory is you never drain the queue. You're a delay pipe, simply adding delay in. And if you want fast interactive networks, big queues and cubic are the wrong way to go. Oh, so I need really short queues. Well, yes, but not too short. Because if your queues are tiny, you get no bandwidth at all. Because every time you kind of get to loss and back off by half, you back off way too far. You actually get idle capacity while you're ramping back up again. So there is a sweet spot around buffer size. So it's not bandwidth times round trip time. That doesn't really work. You shouldn't be doing that because in essence, when you get lots and lots of people trying to share a pipe, they don't all synchronize their behavior. They don't all pile up and oscillate at the same speed. Like the one on the right there, they tend to behave asynchronously. And if they're doing that, the available bandwidth actually drops. So what you should be really asking yourself, and if you're running a long distance network with speed, you should know this number. What's the number of flows that you're currently supporting simultaneously? If you knew that, you know how to dimension your queues because it's bandwidth times round trip time divided by the square root of the number of flows. If you're taking 100 flows, you actually need 1/10 of the bandwidth delay product in your queues in order to push up an optimal queue size. How many people do that? Bugger all. I don't know why, but you know, it's the most expensive piece, or the second most expensive piece of memory in your box, but none of you do it. Maybe because your vendor keeps on telling you you need more. But do I even need that? What's the right protocol to actually get TCP to run maximally fast? So buffers work for two reasons. One, a lot of machines are badly behaved. If you've got available bandwidth, you pump it into available data, you pump it into the network at full speed. There's more sort of speed at the edge. You tend to stress out the network. I've got to even it out. I need buffers. I also need to multiplex, but that's the real problem. Sender burstiness is the real problem here. So stop bursting. If you're running servers, if you're in a data center, everything should be fair queuing. Everything. Because if you don't even out your sending rate, you get shit performance every single time. So the first absolutely golden lesson is almost without respect, which queuing control protocol you're using, always do fair queuing. Even the load on the network, and you stop queue burstiness. If you stop queue burstiness, the end-to-end flow control protocols have a much, much better chance. So if everyone did that, the amount of buffer space you need drops dramatically, in the order of around log of the flow window size, which is really tiny, really, really tiny. Why? Because like I said, routers are expensive because of memory. High-speed memory. When was the last time memory got faster? 2003? 2004? Hasn't got any faster. There's more parallelism, but the cycle speeds of memory are about the same and have been for some decades now. High-speed memory is really expensive, linearly expensive. It's not going to get cheaper. The silicon world can't make it any better. So in other words, that's one of your expensive components that as you go higher and higher speeds in networking is not going to get cheaper. The funny thing is, if you do it right, you actually don't need that much memory. The end-to-end protocol can do it better. The other thing is too, if you look inside your switch, where is that memory? Because the cheapest place to put it is on the switch, in the same chip fabric, in the same chip. But I've only got around 16 to as much 64 megs of memory on board the switching chip. Now, if I can get away with just that much memory, that's a really fast switch. If I have to outboard the memory and put it behind a memory bus, all of a sudden the data rate just slows down like crazy. So the more memory you try and put in a switch, the more you're forced to go off chip, the slower it gets. You kind of ask yourself, why am I doing this? It doesn't make much sense. If you can do this stuff with tiny amounts of memory inside the chip, you're winning. So let's go back to this end-to-end protocol again and understand what's going on. I don't want network capacity lying idle. That's easy. So I don't want underutilized networks. I don't want everyone getting a shit performance because then they all resend, my efficiency goes down, so I don't want saturated. I need to work at what we'd call an optimal flow rate. What is that? Well, here's a little graph of the behavior of a flow. You start to fill the wire, the bottom graph, and as you put in more data, the data gets transferred until you've reached wire speed. And then you can't go faster. The more data you pour in, the more you start queue formation. You're going no faster. So as you start to pour in more data, your delay goes up, but your throughput remains the same. Until you get to the other end, the queue is full, you drop packets. So packet drop says, holy shit, I've broken everything. This is unrecoverable. Where you want to be is that point that says you're filling the wire and you're just touching the queue. So you need to detect the onset of queuing, the onset of it. Now there's this proposal out by Apple, L4S. Comcast has signed up to it. Reuse some bits in IP and TCP. You get the routers to mark packets that say, I'm queuing now, I'm starting to queue, I'm feeling the pain. Oh, TCP session, back off. What about UDP? Well, it sucks to be them. In TCP, it says, I just received a packet that said the router's got a problem. Let me use the TCP ACK to signal back saying, slow down. How many folk deploy ECN? Well, not very many. It's kind of an idea that's been around for, 50 odd years? First started in DECnet, if you remember that far back. And quite frankly, it requires a degree of cooperation between user and network that doesn't exist. If you really want to be a pain in the ass and you're running an ISP, mark congestion on every single packet you're passing through, and the end user, particularly if they're on Apple, will be running at pace that's glacial within a couple of round trip times. You know, it's a really bad idea in some ways because, quite frankly, network signals without authentication are a terrible idea. So ECN just doesn't work. Very few people do it, about 2% around the world, probably because it's a bad idea. How else can we do it? Well, the other way is to try and use a protocol that tries to detect the onset of queuing. And that's the idea behind BBR, the bottleneck bandwidth protocol. That what it does is carefully measure delay. And as soon as delay starts to increase, what does that mean? Well, it doesn't mean a different transmission path. It means that queuing is happening. Queuing is delay. As soon as I sense delay, I kind of pace off just a tiny bit. And that's the idea behind BBR. The way it does this is to see if queues are going to form, it sits there with a very, very large mallet and it increases its sending rate by a phenomenal 25%, which is a huge sending rate increase, and smacks the network really hard. And then it carefully measures delay across that period where there was 25% more traffic. If delay goes up, the answer is, well, I better slow down again. So it does. If delay stays constant, the answer is, woohoo, there's more capacity. I can increase this by 25%. So this protocol is kind of weird. Every 8 round trip times, it pulses into the network, tries to see if there's more capacity. If there is, it lifts its bandwidth very quickly. If there isn't, it goes back to doing what it's doing. So what you find in that low area is the queue occupancy is short, sharp pulses, 1 per 8 RTTs. What does this mean? This stuff is a mammal. This stuff just simply pushes the network as far as the network can go and tells all the other sessions, you've got a problem, because it's exerting a lot of pressure on the network very efficiently. This is a 2-session thing that I did that's simply cubic and BBR. I think it was over a long delay from here to London or somewhere. And as soon as you start up BBR, the other sessions tend to die out. So this is a case of if someone starts doing BBR, the rest of you better start doing it straight away, because you're all going to die if you don't. The point about all of this is that life is changing quite quickly. And what we're seeing right now is a huge amount of evolution in thinking about the way we do networking. And some of the old ideas that we had around flow control, algorithms, the amount of queue space in your buffer, etc., don't really work that well today. There are lots of ideas, cubic, Reno, lead-band, BBR, so on and so forth. Quite frankly, I think very few of them fundamentally change the world. BBR is one of them. Red, weighted red, Codel, fair queuing. Fair queuing is the key. The rest are kind of fluff. Fair queuing is everything. And those two actually do make a huge difference. And what about Apple and L4S? Oh, God, I'm not convinced. I'm really not convinced. So is this protocol Darwinism in action? I think it is. Because what you're actually doing is saying, well, efficiency is possibly more important than fairness. Using available network capacity when there is as efficiently as you can is actually the winning strategy. And protocols that make minimal assumptions about the network and just simply gently prod every 8 RTTs does a better job at it. And if you're really trying to move data around, this stuff works extremely well. So if I were you, fair queuing and BBR will actually win. There's a deeper issue, though, that we don't know what we're doing. That a lot of this stuff is not the theory of networking, it's the observed practice of networking. This is kind of the best ideas we have of how to make stuff at a distance work efficiently when I have no control of the path in the middle and very little control of the thing at the other end. I'm trying to control myself to behave as efficiently as I can to sort of get my fair share and a bit more of the network. Will this change over time? Probably will. Are there really interesting research questions around this area? Christ, yes. There's a whole bunch of stuff we don't know about this. But I suspect that this area and QUIC, which ties in with this, are the two fundamental innovations on the internet that have actually changed the way the internet works. The rest of the stuff, including V6, is kind of boring mechanics. It's not a fundamental change to the dynamics of networking. It's just different packaging of the same bits. So the good news is there's a lot of unsolved problems out there and they still abound. And working on them is a heap of fun. So, any questions? None?
Yay. It works.
BBR V3, they're still developing that, or is it developed? And what's the difference between BBR V1, which I know...
Sorry, there is a live stream, so the mic.
Okay, so the thing was,
There's a mic.
BBR has gone through version 2 and version 3 since version 1. The issue around version 1 is that a whole bunch of network operators of varying size and data center operators said, hell, we're not running BBR. If you're running BBR, Google, we're going to get slaughtered on the wire. For God's sake, turn it down. And so BBR v2 came out after a few years that kind of turned down its aggressive behaviour. It became too apologetic. It gave away all the bandwidth. In the world of trying to be equitable, it lost every fight. And so then they did BBR v3, which sort of returned back to the old V1 style behaviour, relatively aggressive. Is it as good as V1? If you're selfish, I want all the bandwidth, it's close, but V1 is better. If you're everyone else trying to live with BBR, V3 gives you slightly more oxygen to work with. V1 gave you none. It just slaughtered everything. So if it's you, run V1. If it's everyone else, run V3, run something else that isn't slaughtering me. So it's an interesting dynamic about fairness, and that's the story behind it.
Any questions?
By the way, this works over all kinds of round trip times. Now, if you think about it, 90% of your traffic is going 10 kilometres down a last mile network. That last mile network is predominantly radio and predominantly shit. You don't get much capacity out of it. Why not? Because cubic really doesn't handle radio very well. If you really want to make the radio operators cry and weep and completely consume their network, change the way you push the data, and you will start to get a whole much more throughput through that last mile radio network at very, very high speed. Word of warning, if we actually take this advice, they've got a problem. No radio operators in here, are there? No, none.
Hey, one question.
I guess for those of us in the room who are operating the wire, or in some cases the radio part of it, we can't change which TCP algorithm people are using to push the data over this. Is there anything that we can do other than making sure we don't have ridiculous sized buffers to kind of encourage the uptake of BBR or other solutions?
If it was just BBR using TCP, where the TCP control headers are unencrypted, you would use the standard packet meddling approaches, to which the radio and mobile industry is renowned. Google watched you doing this and Google got annoyed. And so they invented QUIC. QUIC encrypts everything, including the control channels. All of TCP is behind the encryption envelope. If I'm running the magic combination of QUIC and BBR, you just simply need to sit back and enjoy it. There's nothing you can do. Everything is opaque. You can't meddle with the entire flow control system. It's just encrypted packets over port 443. Yay. So that distrust between applications and services and the network has reached a complete breakdown. We're not talking to each other. Each regards the other as a bunch of wildcat bastards who are trying to steal whatever it is of user traffic. And quite frankly, all the processing power, all the economic power is on the side of the apps. For you network guys, just add more bandwidth and enjoy it. No other questions? You're all going to add bandwidth, right?
I have one slight thought. So, QUIC is great, but it's not universally applicable. So one thing that you can do, I don't know if you've seen this, is but you can basically you can hide your UDP packets in TCP so that they get treated to the same approach as BBR. So there's a couple of different tunnel protocols that do this. So to your network as the operator, it looks like a TCP packet, but to me as the user, it's actually UDP. So I can put my WireGuard tunnels over it and you can't do shit about it, Mr. Operator. So there's a couple of ways you're going to see this on your networks if you haven't already. It's fun.
the current technology fashion, and we are fashion driven, we're very stylish people in the networking world. The current fashion is to put everything in QUIC. Everything, video streaming, you know. The thing is, QUIC does both flow control, reliable UDP, unreliable UDP, multi-streams. It does everything we wanted from TCP 30 years ago. And quite frankly, for that reason alone, we're all trying to put everything into QUIC, including BGP. Be very afraid. No other questions? Oh. Someone who's offended by putting BGP in QUIC, I would be too.
Thank you, Jeff. The question I've got is, have you played around with using tools like stochastic fair queue to kind of police BBR versus other TCPs?
Oh, it's really hard because...
And can that ever scale?
BBR doesn't always check the queues. It only does it every 8th RTT, and it's over like that. So if you're looking at your queue, you might never see that BBR pulse. It's just come and gone. And the usual techniques of queue management, average queue occupancy time, blah, 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 don't work. And so the challenge of trying to modify your queue behavior to kind of fool BBR, good luck, just good luck. And in a high-speed, large-volume network, I think you're going to lose, is my bet, but, you know, try it.
Thank you.
Yeah, regarding the, you know, having to use UDP over, I mean, TCP over UDP, it's good, but the problem you end up with is that the congestion control, back to the issues that you had on the different TCP versions or variant of TCP. I did a similar work, research days, and the problem we have is that even though we invent different variant of TCP and try to experiment and see which one works, back in those days, satellite was so slow, and TCP can't survive on high latency networks. The solution is obviously add more links, as you mentioned. But the problem is that that doesn't apply everywhere. So maybe operating systems need to adjust the different variants of TCP.
Oh, look, we played around with proxy accelerators, proxy agents. There's talks from Van Jacobson about high-speed TCP over satellite from 30 years ago. It doesn't work. Hughes tried to do it with their satellite solution 20 years ago. It doesn't work. In an adaptive system, I need to know how my packets are going. And the only way I can know is to get feedback from the other end. Now, if it's a long delay path, that feedback is slow and it's difficult to adjust. If it's a short path, brrr, I'm just there. You can't get over physics. You just can't. If you want really, really, really high speed AI, move to the same data center. We are. And there you have it.
Cool. Thank you. We'll wrap up questions there, I think. Thank you, Jeff.
Thank you.
Okay, last year NZNOG started hosting a sisters event as a way to get more women coming to our conference and in our industry and giving them some useful skills. Next up we've got Sabrina. She actually works for the Internet Association of Australia, who are massive supporters of sisters here and basically run it for us. And so anyway, Sabrina's bringing a couple of friends onto the stage and talk about sisters.
Thank you, everyone. And I really mean thank you, because without the support of the entire community, we wouldn't be able to run this program here in New Zealand. Just to give you sorry. No, it's okay. I can go without the slides to start. I just wanted to give you a quick update on where we are with Sisters. So this was our second Sisters we've hosted here in New Zealand, which makes our 7th program overall so far. I'm proud to announce that we have over 100 alumni now in our cohort across Australia and New Zealand. And we're always looking for ways to grow the program and keep in touch with them. In Australia, we have a board mentorship program where they shadow our board chair. We have an alumni speaker program. And as we grow here in New Zealand, I'm hoping that we can do something along the same lines. Again, as I said, this wouldn't be possible. I don't know which clicker I'm using. Wouldn't be possible without our sponsors. So while many people support and are supportive of the program, these here are the companies that got behind us this year, and we wanted to say a huge thank you to them. And in that vein, we have now opened the program for next year for both applications, sponsors, and nominations. So if you have anyone that you are working with that you think would benefit from the program, or you have a company that would like to support the program, I'm here all week. I'm happy to talk about it. I think I've talked a couple of people's ears off already. But we are thrilled to be running the 3rd program with New Zealand next year when they go to their next location, which is yet to be announced. So the program has a couple of key takeaways. It is a soft skill workshop. We have a career coach who kind of gives them some advice, and we have presentation skills, which helps them upskill themselves for their careers as they are. But that's not really what the best part of the program is. It's about empowerment. It's letting them believe in themselves, that they belong in this industry, that they have the supporters, and it's really about building their network because, as you know, on your teams, if you have women, there might be 1 or 2, and so they work in silos a lot. And so this just gives them a broader network across the country of people that they can lean on as they try and navigate their careers. And this is this year's cohort. And so I'd like to ask any of the sisters in the audience to just please stand up to let people know who you are so that they can introduce themselves to you, you can introduce yourselves to them and continue networking. And I see you and I know you're shy, but you can do it. And in that vein, we are trying to encourage more women to get on the podium, like ask to come to the conferences, first of all, because that's part of the problem. They don't ask, they don't get. But once they're here, we'd also like to see representation on stage. And while I know that we have a speaker tomorrow, and I'm up here, I thought, I'm a talking head. I can tell you how awesome this program is all day. But these are 2 of our sisters from this year who would just like to share, or have asked to share, or voluntold to share their experience, so you can kind of get a taste firsthand of what it's like to be, for one of these women to come here and have this experience. So I'd like to introduce Pooja first.
Kia ora. My name is Pooja, and I work as a systems administrator at Internet New Zealand. Thanks, Sabrina. It was an awesome presentation. I would like to mention that the IA systems program is not kind of a technical framework that we women will learn all about technicality in one day. It was more of a mindset shift that tells us that community is the driving force behind all women's success. And this program, I have got many takeaways from this. The first is when Alexia from Girl Boss New Zealand was giving her presentation, she mentioned one phrase in her presentation, that find your sparkle. Finding sparkle doesn't mean we have to shine bright in the room. It just means that when the world falls apart, we just have to find strengths, find colleagues, find our connections that are going through the same, and they uplift us. So that was one takeaway for me. Another big takeaway for me was asking the questions. I wouldn't say asking the right questions because every question is right. So asking the question was really important factor to build your success. Second thing was asking for the opportunity, asking for the pay rise, of course, asking for the opportunities that men's get. Sometimes we women lag behind. So ask what you need, ask what you should ask. This was the second major takeaway. Thanks. It is not a sales pitch. Thanks, IA Sisters, all the sponsors, and all women sitting in this room. Please ask women in your org to come and attend this program. It will really help building their success. Thank you.
Thank you, Pooja. And the next person I'd like to bring up to just say a few words is Chris from Chorus.
Kia ora, everyone. So, let's all imagine you're in a world where you just started doing IT hardware sales, and you finally got the courage to go up to your boss and go, hey, I'd like to learn how to deploy this hardware that I've been selling. And your boss looks at you and goes, you know what, you're a girl, just dress pretty, look pretty, bring in your pre-sales, he'll do the job, you don't have to worry a little head over it. Bit painful, eh? Now, imagine a world where you've got a different world where your boss and your colleague is the one who is there to support you, who wants you to succeed, who wants you to, to just believe in yourself a little bit more, and who is willing to put your name forward to do that. Then imagine being in a room full of amazing, enthusiastic young people who, well, not all very young, but some young people, who are willing to, who just want to learn and who have just as much passion about technology as you do. And then imagine having the opportunity to know these really super smart, super talented people who are not just there to give you the expertise, but they're also willing to extend a hand to help pull you up because they want you to succeed with them. And that, to me, is IA Sisters. And that is Chorus. And I'm very happy to have my colleague and my boss who have supported me so that I could be here this week, sorry. So if you know someone who could do with a little kickstart, who could, do with a little bit of inspiration, or maybe they just need the words to say, hey, I believe in you, and I'm here for you. Or even better, if you're in a position where you've got the ability to say, hey, I'd like to be able to enable someone else to have that spark lit up in them, then please nominate someone for next year's IA Sisters Conference. Registrations are open. Or even better, just become a sponsor. Because to me, every fire requires a spark to start, and some of them will glimmer, some of them will turn into this raging flame, but I believe that every single one of them will make all of us stronger. So nominate, sponsor, and let's keep this fire going. That's me.
I'm going to ask that you give one more round of applause for Chris and Pooja because they didn't come to New Zealand or come to this conference thinking they were going to get on stage and have to address, 300 people. I kind of said yesterday, I'm looking for volunteers, and when no one put up their hand, I sought out people to volunteer. And so I think that they did a really great job, and they really actually put in play the things that we were able to teach them yesterday with our amazing speakers. So one more hand for both of them, please. So again, thank you so much. We are partnered with NZNOG, and we are so pleased that they believe in this program so much that they were willing to do whatever it took to get us here. But without the support of the broader community and the sponsors in the community, we really couldn't run this program. So thank you very much. I am here all week, and I would love to talk to anybody who will listen to me about the program. I know my board chair, Matt, is like looking at me and laughing. It is my passion project. I love it, and I would like everybody else to get on board and love it as much as I do. So I'm Sabrina, and I'm looking forward to talking to all of you. Thank you.
Cool, thanks, Sabrina. We've got NZIX next, giving an update. I'm actually a committee member of NZIX as well, as probably most people know. We've just had our 10th anniversary, so we've been running Auckland IX for 10 years now, so we've celebrated that. We've got these new hoodies, which I'm modelling right now. We're almost out, I think, but there's still a few for our members at the NZIX stand out there, so if you don't have one and you want one, go see Tans and Co there. But yeah, now and actually there's code on the back as well. It's not random zeros and ones on the back, so tell me if you can decipher the code on the back of these hoodies. But anyway, without further ado, we've got Aaron. He also hails from the West Island. We don't hold that against him too often, but he's going to come up and give a bit of an NZIX update, including exciting news on automation, maybe. Anyway, thank you, Aaron.
Thanks, Dave. So I'm Aaron. I work for Internet Association of Australia, and New Zealand Internet Exchange contract us to operate the thing. I try not to assume baseline knowledge of people, so bear with me for this first topic. I'm sure everyone here knows what Internet Exchange is, but this is for the people that don't. An Internet Exchange, primary purpose is to facilitate the interconnection between networks. And New Zealand Internet Exchange, any exchange that you see, primarily just has a bunch of switches connected by cables to another data center. We operate specialized servers called route servers that you basically peer with to announce your addresses, your IP addresses, your routes, and that server reflects back routes of everyone else. You as a customer, you connect to one of our switches, you give in peering addresses, and then you do one of two things, or both. You connect to the route servers, you share your routes, and you get everyone else's. And then that's called multilateral peering, or you connect directly with just one neighbor, and you share your routes, and you only receive theirs. Simple as that. That's called bilateral peering. Exchanges are generally just metro connectivity only, and the point is to keep things local and really fast. There's a lot of exchanges. They range from non-profits like NZIX to private corporations that are small, multinational, to data center operators that run an exchange as part of their own thing. Now, why peer? In Kevin's famous words, why waste time, say lot word when few word do trick? It's one port, many peers, low cost, and it's a giant highway. It vastly reduces your transit utilization. And the best case I can see here is from Leaptel that did a preso in Apex about his split. And as Matt went on stage earlier, he's over 75k subs now, which is awesome, and 350 gig peaks, that's sick. But he's seen about effectively 88% of his traffic go across peering. That can result into a massive reduction in tube transit. So for a lot of people, it's just a no-brainer, but for the people that aren't really aware of it, that's why peering exists. It's a massive reduction in your transit, plus it's just a high bandwidth highway. Right, so on to the IX update. Each year we do kind of just an update of where things are at with NZIX, and this is no different. We have the exchange recipe, so what it consists of, and this is the current state as of right now, so not much changes since last year, besides we've moved 2 exchanges to EVPN VXLAN, and so the Ethernet fabric for Auckland Exchange is VPLS still, and with some traffic engineering, we're going to move that to VXLAN soon. and more on that later. Switching hardware is just extreme networks, 32 by 100 gig ports, boxes, optical, flex and smart optics, fiber carriers, Eon fiber, which was 1NZ, and Chorus. Route servers, just a bunch of Dells, and running Bird as the BGP daemon. We have port security rules, so you can only have one MAC address per peering service. We do some ACL filtering, things like that. It's pretty standard for an exchange. On the provisioning side of things, we have a portal that we've developed in-house in IAA land. That is something that we're looking to sort of open source eventually to be a competitor to IXP Manager, which is the default off-the-shelf tool for most IXPs. And a lot of development has gone into that. So that's where your audio services manage your things, etc. The actual portal and things like that live in SiteHost, so that's a VPS provider in New Zealand. And that's where our Kubernetes cluster, all the apps and things all live. So we have a staging cluster as well as our production. To manage the network, this is new over the past year, so we've moved to Tailscale for gluing between SiteHost to the network, and that's just using dual subnet routers in different Proxmox hosts at each site. Out-of-band boxes, just open gears and backhaul paths. We have Trustpower, Mercury, and InspireNet. But obviously the most important ingredient of a peering exchange is the members. That's the most critical thing. Once you get all the members, you heat critical mass, and it just makes more sense to connect to an exchange because everyone's there. Moving on just to overview of each exchange. Auckland IX, not much changed since last year. And 5 points of presence, 220 Queen, MDR, 2 Degrees Albany, Datacom Orbit, and DataVault Grafton. NZNOG 2022, we did an upgrade to like a 400 gig ring, and that's been consistent since. There's been no big structural changes there. Plans for the future, different sites. We're looking at NextDC AK1 once it's fully up. That's obviously, this is all tentative. And then 400 gig is on the roadmap, as well as moving to VXLAN as well. So traffic over the past few years, we're seeing consistent increases year on year, which is good to see. In the blue, we have 2023 to 2024 March, and then same yellow, 2025, and green is now. So Auckland IX is going really good. And we want to keep that growing. This is in line with our sort of predictions based with the 400 gig plan that we did in 2022. And now is coming closer to actually build a new core, basically. Moving to Wellington IX. Only recent change in last year was moving to VXLAN. Nothing too special there. We just 2 boxes, 2 sites, diverse fiber, and tentative plans are looking at different data centers, but more on that soon. Traffic peaks for Wellington. So these are 1 minute intervals with our matrix data of just the maximum of that, within that minute. And we can see green is the most recent, and it's starting to pick up a bit more of 30 gig per second peak days. Moving on to Christchurch. We moved to VXLAN for this. We also deployed 100 gig hardware. That took forever just because of, we wanted to wait for dark fiber to land before we did the thing, and it just took quite a lot longer than expected. So now we have diverse fiber between sites, 2 POPs, and we have tentative plans for different data centers. Here's the traffic levels for Christchurch, and there was one peer that shifted traffic away in 2025 just because of we didn't have the 100 gig availability, but now that's there, we would expect them to come back. So each one of these had their own sort of future plans, but we really take member input seriously. It's a non-profit, we take direction from members, we bring that direction to the committee, and we say, hey, 20 people have said they're going to build into this data center. Let's deploy there first. Let's get there before everyone's there, and then they can all plug in when it's there. So if you're looking to build to a different site, if you are, looking at those future plans and say, oh, I'm actually there, I would love to just send my voice. We do have a propose a pop form on our website, and that, fill out that form, it'll come to us, and we register that. Same as any other product. If there's anything else that you think the exchange should do, there's the concept of running an auxiliary content network where we host Netflix caches, we host Steam caches and things like that. We do this in Australia, but New Zealand hasn't done that yet. That's not something we're looking to do right now, but it is on the radar, and if that's something that members want to see, that would be beneficial. It's a hard balance to play between running the cost of those things, those auxiliary networks, and then we have content providers that come in that really only want peering. They don't care about these extra things. So it's just finding that balance between that can be difficult. So and then of course, is there any other product? Just shoot us an email. Okay, so that's it for the IX update. Now the fun stuff. Okay, so it's 3 a.m., your MikroTik has blown up, you've gone to site, you've replaced it, and you're sitting there in the rack waiting for your MAC address to be updated. Because you've emailed them, you said, hey, please update this MAC, I need this back online. You watched your transit link go way past its commit, and you're going to be hit with burst charges for that month. Or you're congesting and now you're getting lost. This sucks for you, your customers, and us. That's why I'm very happy to announce that we do have service automation for New Zealand Internet Exchange. We've enabled that as of 9th of March. We just kind of did a soft launch. There were sort of slight growing pains. We haven't had any major things yet, which are good. There's been a lot of testing, a lot of development behind it. But yeah, it's finally here. Basically, the past 6 to 8 months, we've just worked every week on each task that we wanted to do. We wanted to try our best to automate as much as we possibly could. So that starts at the port orders. As soon as you order a port, you get an instant LOA, and you also get the port is actually configured and deployed immediately. We had a Cloudflare port ordered the other day, and the data center operator called me within 30 minutes saying, hey, we're not getting any light, but he was looking in the wrong direction. It was actually the other side. So, port upgrades, converting your port to a lag, adding additional ports, that's all standard, automated, and peering services as well. So IP address allocation, that plugs into our NetBox instance. BGP session configuration is just deployed, pushed through Ansible. And then peering, VLAN, and MAC address changes is done through our automation application called Stanley. As well as service migrations. If you move into a different POP, you send up a new port, and then you can migrate that within the portal. Cancellations as well, but because of our structure of the billing period, we do some crediting, but that's it. We can do all the things. This is what it looks like just on the portal side. Green is good for automation. We have feedback stuff to the users, so if there's maintenance happening, we will, it'll be obvious there that, hold up, you can't do this change right now, we're doing something with the site. It provides instant feedback of the route server deploys as well as your change request actually progressing. So it's been a big milestone for us, and we're really happy it's here. So I can focus on other fun things. I'm curious how much time I got, but 2 minutes, guys. I got 2 minutes. Well, I'm probably going to skip this other one, but this one, this is just our roadmap that we have. It's tentatively scoped, and this is kind of what we want to do for the next few things. So now that automation is in, we'll be iterating on a few things with the automation, but we'll be looking to implement health status stuff. So putting live status of your links, congestion, stuff like that, as well as peering status, as well as we want to index. If you're missing bilats to a content provider, there'll be content providers that peer with a route server, and they share most of their routes. They don't share all of them. you can only get that through a bilat to them. So things like that, just to make sure everyone's getting the most out of their peering, is something that we want to put into the portal, as well as like flow metrics, so you can just see the last 24 hours of the top talkers between you and whoever else. Notification system is the next thing on the list of things to do, and that's just plugging in notifiers to people. So you could push it to your Slack or whatever for each thing, and just some maintenance stuff. Product-wise, so New Zealand is looking to deploy 400 gig member ports. So that's the next sort of big sort of thing that we want to do. And there's a bit of a roadmap for that. There's also virtual lease lines, so virtual cross-connect. Now that we're automated, that would be super easy for you to order and cancel, etc. And then a secondary peering service is another product that's on the roadmap. Just bringing you could bring your customer layer 2 back to them, and you can bring them onto the exchange. I won't go through this. I think it probably has its own, it's got enough things to have its own sort of talk and break it down properly, because it probably is justified. But I'll leave this up here for anyone that just wants to skim through. But this is basically the past 6 to 8 months of the development work and what we needed to do to get it to the system that it is now. Having like a demarcation system that we can import verified ports, so you can instantly order a port, but then that yells at us and says, hey, you've got to go patching, we've only got 200 gigs left at the site, etc. As well as a bunch of admin tooling to make it so we can go to a site, if we're switching from one vendor to another, we can just plug in the new switch, press a bunch of buttons, it pushes everything across. All we got to do is read code optics and put it over, and that's it. A bunch of security things and automation sliders. Right. So 400 gig is the next thing for Auckland. It's been it's in the approved stage, and now we're in the interop testing phase. NZNOG 2022, I requested from the Treasurer a lot of money to get a diverse ring. We basically previously had a lot of paths to the northern end of Auckland across the harbour bridge, and that was kind of like an issue. If we had a break on there, we lose communication that way. So re-architected the thing and basically made a very long western path, and we lit that up with coherent 400 gig optics. 2022, very expensive. They've come down quite a bit, but still pretty expensive. So here's a picture of Dave Mill. He has more hair, but yes, it's the same thing now, just with a new treasurer. So Nathan Brookfield is the new treasurer for NZIX, and I'm going to ask for all the money to do the thing right, because we're a non-profit, right? All the money that we get from people needs to go back into the network to do the thing. And if you're wondering where timeline-wise we are with this, we kind of crashed the box, but we are at formal interrupt testing. And hopefully the next 2 weeks I'll get some time to lock in and get the tick box, and then we can get stuff ordered. Proceed with migrating Auckland IX to VXLAN, and then plug in the new boxes and get the new ring up, which will be probably a 1.6 terabit ring, but should never hit buffers. We don't ever congest. We upgrade before we hit 50% utilization, so there's always ample capacity available. And that's it. Any questions? Sweet.
No questions by the looks. Thank you, Aaron. Cool. Thank you, everyone. It's now our lunch break. Just a little reminder, in your bag of swag, you've got a little Mercury box. It's got a unique number on it. Go see Karen and anyone else at from Mercury at the Mercury kind of banner out in the food area, and they'll be able to tell you if you've won a cool new phone. Other than that, a bit of a reminder about the buses. Tonight we're heading out to the Wigram Air Force Museum for a bit of a tour and some drinks and some dinner. Buses depart from 5:30, don't be late. I think there's 3 buses go out, don't wait for the later one. Other than that, lunch is now, and we're reconvening at 1:30 on the dot. Enjoy. Thank you.
Alrighty, looks like everybody's back in here now. You people trying to find seats at the back, there's more seats up the front. You know, you're welcome to come. You don't have to turn your head too much. Up next we've got Don Stokes talking about the life of a 90s ISP.
Okay, thank you. So this is basically about my life in between 1992 to 97. Just a bit of background, the Victoria University's Computer Science Department started bringing Usenet, UCP, Usenet email and news in around about 1985. And that's where quite a few people got their first sort of internet touch, even though it wasn't actually IP. In 1989, the PACCOM group got set up, co-funded by NASA to get connectivity around the Pacific Rim. And for New Zealand, that meant a 9600 bits per second analog link over the old ANSCAN cable, analog cable, big copper thing like this. It got upgraded up to about 14K over time, and in the meantime, initially the university's computer science arranged a link to Waikato via some mess involving the DSIR network. And in 1990, Kawahiko network was set up amongst now via the actual university IT departments on 48K lines. There's a picture of that further down. In 1991, we got that link up to 64K over a satellite with everything that meant. Meanwhile, I started out on 8-bit micros in the early 80s, graduated to dinosaurs like this guy around about 86, came down to Wellington at the government printing office for a bit, and then Vic advertised for a network systems manager, which I applied for and obviously got, otherwise I wouldn't be here. That little yellow cable is how we did networking in the 80s. Big yellow Ethernet hose, 10 megabits. So this is what I got to when I got into the place in January 92. The map is the Kawahiko network as it stood at the time. I don't know much about the MAFnet or the DSIR net, just that they interconnected at Waikato. We still had, we were still on 64K satellite. We had DNS running at Waikato and Victoria. And we had about 6 external connections, mostly via analog modems on copper leased lines at typically 9K6 or 14.4. And we were starting to get some interest in all this. In this time, Victoria University had a very liberal approach to who it allowed onto the internet, and our usage was the highest in the country. So in 92, we saw the research sector reforms where the Crown Research Institutes were set up out of the old DSIR. That happened about mid-year. And in the wreckage of that, we saw the DSIR network pretty much come to an end, and the TUIA network replaced it. So it also replaced Kawahiko. We connected 128K bits. I can't remember what Waikato did. I think they had 256. Auckland was 128. That was happening, and in the meantime, I also had a bit of a problem with the way we were doing external connections. Those slip links were all into the back of old PCs, acting as PC routers, and some of them were big and taking up a lot of space on the floor. I also had only basic dial-up at the time. We only had a couple of 9K6 modems, not even 14.4. And I wanted to be able to do things like slip IP, dial-up IP, and so on. Cisco came out about that time with a thing called the Cisco 516, and I said, I want one, and I went to Frank March, who was the director, and I said, I want this, and it's going to cost $8,000, and he said, I haven't got any money, and I said, come with me. and took him to the pile of Commodore PCs that were sitting in the workshop and said, we're going to sell those. So we had a garage sale, and that's how we bought our first actual piece of internetworking hardware. As the year progressed, a few things happened. One is that the Waikato folks got to grips with how they were going to charge the rest of the network users for international traffic. We'd sort of kind of fudged it up to that point. So we had a sort of a volume tier. We talked about it as volume charging, but it was actually a bit more complicated than that. I'm dropping out? Okay. So we were now starting to worry about how our usage was going to impact our budget. And around about that time, the CityNet, which was run by Richard Naylor at the Wellington City Council, was starting to offer things like downloading via FTP and then letting people sort of use Z-modem or whatever to download the file that had been brought down to their PCs, and the usage was just on a very rapid upward trajectory. It got to the point around about November where they exceeded the amount of traffic that the university was doing. I said we were the biggest user. Well, most of the time that was true, but not that month. So at this point we went, we can't keep doing this. We've got a choice. We can try and run down what we're doing and just say we're not going to do this anymore, or we can charge silly amounts of money to make people go away, or we can see if we can make this sustainable. So we set up what we called the Victoria University Internetworking Group, which was mostly me. And we basically said, look, we will charge you a nominal fee to have access. We will on-charge effectively the traffic that you're using. And that was basically a volume charge at this point. And you pay the communications cost to talk to us. And that was the model. Kicked that off basically from the start of '93, and around about that time we saw the PATCOM link finally go up another step to 128k, still on satellite, still with 700 millisecond round trips. So that carried on, and the demand increased over that time. By 1994, the university, we'd had some reorganisations in the way the IT was structured. Frank March was now the director of the new ITS that had replaced the Computing Services Centre, and our budgets were now coming through the registry, and we couldn't sort of hide this anymore. So we were ticking along at about 40 odd leased lines, about $250,000 turnover. So we started discussions on commercialising the operation with Victoria Link Limited, which was a company that the university owned for doing research to industry and so on. Meantime, the subsidies we were getting, that the international links were getting from NASA, ended around about beginning of '94. The PACRAM East cable was finally commissioned, or 1 gigabit worth of it. And early '94, we saw PACCOM go to 256k over that fibre. So we finally launched a NetLink in 1995 in April. We offered basically what we were doing, but with the addition of dial-up lines. So we've got 24 lines worth of modems in. Basic email hosting, basic web hosting. Stuart Wilson was working for Victoria Link, and did most of the commercials. I looked after the technical. At about that time, we'd also brought Sid Jones, who some of you may know, on as our first ever actual employee for the internet. So '95, we slowly expanded, rapidly expanded actually. We took on Auckland University's operation. So Neville Brownlee at Auckland and I have to say we were almost always on the same page on a lot of the stuff. We were buying the same gear, having the same issues. We talked to each other all the time. Our charge models were similar. So it was a relative no-brainer when a small ISP decided to attack another ISP during one of their demos. And at that point, Auckland got the jitters about the whole idea, and they wanted to get rid of what they were doing, and we said, come to us. That happened. The expansion to Christchurch was a little different. We were working extensively with Network Dynamics, I'll talk about them in a minute, and we put their stuff into their offices out in somewhere in Christchurch, I can't remember exactly where. And late in the year, Ruapehu exploded, and we decided we'd put a camera on it. Or Richard Naylor decided to put a camera on it, I just did all the work. There's a pic from it. And we were basically taking pictures and sending them down at a stunning 1 frame per minute. The cell phone link that we had out there was really crap. So as we head into '96, the Waikato folks had basically gone, we don't want to be doing this internet thing anymore. They'd handed the whole thing basically to Netway. And that was about the point where we started having to buy our bandwidth directly. $4,500 per 64 kilobits per month. Elsewhere, deployed Hamilton and Dunedin POPs. The Hamilton POP was really to support our connection into what was then NZIX or NZ Gate. And the Dunedin POP was a bit of an experiment because we brought Clear in on as our downstream provider for that. We put in some 2.4 gig spread spectrum radio stuff. It's probably the first time anybody had done that on any kind of scale in the country. Not a lot of scale, but and we put on the first CityLink connections. That sort of happened late in '96. If anybody remembers CityLink. Other experiments included doing encrypted VPNs between the parliamentary complex and internal affairs that looked after them. They ran actual 2 meg connections between the 2 locations and just encrypted it. So they're basically public internet between the 2. I think that was pretty much the first time that had been done. And in '96 was the first MMP election. And I believe is certainly one of, if not the first successful, because there had been some false starts, attempt to cover an election on the web. So we did that. In '97, Netlink was incorporated as its own separate company instead of being part of Victoria Link. The new CEO was employed, Stu Wilson and myself left. I'll leave you to read between the lines on that. David Plummer took over in 1998, and the whole company was sold to Telstra in the end of '99. And I sort of listed the companies that were sort of in that family. So this is what the machine room actually looked like in about '97. You've got on the right-hand side, those 5 cabinets were all Netlink gear. Campus and Netlink dial-ups and the 2 big red cabinets, there's just red perspex in front of it. And the campus network gear entirely lived in that right-hand cabinet. And a closer-up look. So what we're looking at there are mostly lots and lots of NTUs, individual X21 connections into the back of them, copper pair to back to the telecom. Increasingly, we were starting to bring in 2 meg connections and using things like stacked wideband. So you could take a bunch of time slots on a 2 meg connection, call that a 64 or 128 or a 256K or whatever link. We were just kind of experimenting with that at that point. Also, primary rate ISDN was another thing. The little server on the bottom right is the first one we put in. That is originally was a 16 megabyte 486 with a 2 gig disk, and that served basically everything for quite a long time. By the time this picture was taken, a few more servers had joined the equipment. The boxes you can see there are mostly the Network Dynamics / Securicore 3net / Teltrend, whatever they became. I'll talk about those in a minute. A couple of Cisco boxes. The AGS on there that you can see is this original chassis from what had been the CSC router, which was bought in 1989. It was used for connecting up Kawahiko, then was used for outbound internet access. And I still have that box. Telecommunications. Telecom owned everything. Clear was trying, but they had no real stories on the last mile. They put in a few microwave links here and there. We did have one. The cabinet that you can see there, that didn't cost us anything. Telecom put all of that in. That's PDH at 140 megs on the fibre ring that connected the Kelvin and Karori exchanges. 140 megs, you'd take out, with PDH, you take out 4 34 meg links off that, then those could be divided into 4 8 meg links, which could be divided into 4 2 meg links, which we'd either use directly, or the upper two of the 3 boxes you can see there are VMUXs, which we use for dial-up. So we take a 2 meg into those, and that would give us 30 phone lines. Obviously, we were trying to do whatever things that didn't involve telecom that we could. The net radio, the frequency hops, spread spectrum, which I'll talk about, and CityLink, and we had a few other experiments. Marine Air Services had a UHF link they put in. Internally, everything was 10 meg, and shared Ethernet switching wasn't really a thing. We were just starting to experiment with it when I left. Modems. Everybody hated modems. Everybody hated modems with a deep and abiding passion. Initially, we sort of standardised on the ZIX modem at 14K4 or 16.8 if you had 2 of them back to back. They didn't have a VFast V28K story. They were all a standalone modem with a plug pack. At one point, I got the electronics facility to build me a box that just had a whole lot of DC cable, not even DC, they were 12-volt AC cables coming out the back of it. So at least I didn't have a whole lot of plug packs. And then around about 93, the university proposed building a large-scale dial-up facility, at which point I went, oh my God, I have no idea how I'm going to build this. And I was up at Waikato later that year and asked John Hawker what he was doing, and he pointed to a rack of modems he had on a shelf in his comms room. When I say a rack, I mean he had a shelf with a stack of modems on it, just sitting on their sides. And I said, oh, well, what are those? And he said, oh, this company in Auckland makes those, and gave me contacts. So I got in touch with them. I had a lease line I needed to put in, so I bought a pair, tried them out, seemed to work, faster than the ZIXs, tidier than the ZIXs, still had a plug pack. I rang the company involved and said 2 things. One, a couple of things about leased line connections. You won't want to make these changes into your configuration to do stuff like locking down the baud rate so it couldn't possibly change unexpectedly. And secondly, could you just shell them and put them on a shelf? Nothing special, just want a power supply, a bunch of modems, connectors out the back, done. And they went, unlike the people I talked to about the ZIXL ones, they went, oh yeah, we can do that. We bought quite a lot of them. They sent me a very nice, some very nice whiskey one year. We deployed eventually 80 odd lines at, we didn't quite go to 150 that was originally being proposed, but we went to 80 odd lines on the campus dial, and we had about 60 in the Wellington dial and pool at the end, initially 24. Put 24 in Auckland, I think, 12 in Christchurch. I believe they must have kept going after I left. So they were very good. They were, and the first one that I got, I had to pull it apart and resolder some of the wires because they weren't quite right, but you know, you got used to that kind of thing in this game. The other local outfit that we dealt with extensively was Network Dynamics / Secure Core 3NET / Teltrend, as they were by the time I left, and became part of Allied Telesis Labs eventually. And these were based originally on some code that was written in Australia at CSIRO, a thing they called Node code. The DSIR team run by I can't remember his name. They recoded onto the MC68K. They started building boxes that we actually kind of like the look of. You had a basic chassis with a couple of sync ports built onto it, and an Ethernet, 10 megs, of course, and then an expansion slot. And the expansion slot could take 4 more sync ports, or a bunch of async ports, 12 or 16, or 2 E1 telco 2 meg connections, channelized or otherwise. And we bought quite a lot of these boxes. They also had smaller end routers with a single sync hole in the Ethernet that we'd put at the other end. The reliability, these caused me so much trouble. The dial-up pole, so in the picture there you've got the, you can see there's 5 of those boxes, and in front of those are 5 shelves of modems. So I just had the routers on the back and the modems on the front. The modems have, we'd take a 25 pair cable, split it into 2, and they actually built them with champ connectors, so we just put 12 pairs right into the back of the modem, and that was very tidy. The serial ports was just still serial ports, DB25s. And you can see the thin wire Ethernet snaking between them, which was how it all connected together. But these things caused us a huge amount of trouble with the, because they had not done async PPP. They'd been doing synchronous PPP for a while, but they hadn't done async PPP with all of the negotiation requirements that come with that, PAP-CHAP, and the IC. The other one that was particularly memorable was the TCP header compression. They weren't negotiating that correctly, and I had to peel apart packets to find out what was going on with that. And elsewhere we had issues with their OSPF implementation had its moments, and there was a couple of days where the routing table had just got to a size where it had filled some buffer somewhere and it just stopped working. So I had like a couple of days before I could get much of the network back up and running because OSPF just fell over. The guy who was good at it, Tony Vanderpeet, was away, and he was one of his offsiders. And it was clear this offsider had no idea where it was, because not only were the patches he was giving us not fixing the problem, they weren't making it any worse, which is what I would expect if he'd stuffed something up. Net radio was, so we got sold by Radiola this, well, it was nominally 1.6 meg data rate, 2.4 gigahertz, frequency hopping, could do point to multipoint reasonably well. And we set this up with 3 antennas up on the top of the Cotton Building at Victoria University, which, is, if anybody knows it, has a fantastic view over the city. We'd get about half a megabit real-world performance on a good day. We had about 11 customers by the time I left on that, so it wasn't a huge volume, but it was cheaper than a lot of the alternatives. It was a bit faster. I bumped into somebody the other day who was saying, oh, we had this really neat connection act when I was at high school. We had connected up Wellington High School. And I thought, yep, that was good. I built that. We had little PCs that we were getting quite cheaply. How am I doing? So we had little PCs. We were putting an ISA card into the back of those, and they were working pretty well. There's still a pole on the top of Trades Hall in Vivian Street. That's the pic there, and it's still there. It's not doing anything, obviously. But yeah, 2.4 gigahertz for a kilometre was the thing. Good luck doing that today. The web. People don't realise how fast the web took over. We always talk about, oh, it got invented in 1989. Well, yeah, sure, but nobody saw it until 1993. Nobody used it until 1994. Because that was when Netscape came out, and suddenly the browser was actually decent. Fell over a lot, but it was decent. So around about the beginning of 95, I sort of went, well, this is all very fine, but you need to set up a box for a web server and so on. Why don't we just actually put a whole bunch of IP addresses on a box and let people connect to different IP addresses and have the web server figure out which web host they're talking to? You know it as named virtual hosting and Apache and friends, and we did it first. So later in the year, we introduced what we called the Internet Presence Account, where we basically said we'll give you a virtual host, a dial-up account, and so you can actually talk to it, and a mailbox, and we'll sell that to you for $100 a month. Good money in those days. So the environment we lived in, the telecom monopoly on the last mile, realistically, we didn't deal with that until UFB. UFB was to solve that problem. You know, it wasn't about fibre, it was to solve the telecom monopoly. You just did fibre because that was the way you did these things. Telcos were slow to embrace the internet, and not only that, they were, I'll come to that. Internet was very much a nice to have in those days. It wasn't anything like as essential as we were doing. Voice services and nothing else was on it apart from browsing the web and using your email, right? So nobody was making phone calls over it, nobody was watching video over it. So it sort of didn't matter if it fell over for a few hours. So we didn't seismically brace anything. We didn't have backup power. We didn't have extra routers on things. There's a lot of things that you just wouldn't do now. We were trying to deal with rapid growth, so we were just throwing stuff at it as fast as we can, and a lot of things went by the way as a result. And of course, the prices of everything was, as I already said, $4,500 per 64K international. You know, the last time I bought stuff, it was down to a few dollars per megabit. And the equipment costs were still high. Cisco never produced something that I really thought was good price-wise, but never mind. There was a lot of bleeding on the bleeding edge. We had a lot of things that didn't work, a lot of code we had to write, and there was never anybody you could go to ask. You know, nobody had done this stuff before. We found that because things hadn't been commoditized, we were getting better results by using local resources. Obviously, that did have its challenges, but it did mean if you could talk to the vendor, you could actually get what you wanted. That's very hard to do these days. Of course, a lot of things, you know, there were modem suppliers and equipment suppliers. Is that my get off music? Yeah, no, I'm. So telecommunications were complicated, inefficient, and expensive. There was a lot of time to make. TDM gear was horrific, and security, like resiliency, was a bit of an afterthought. We started this because we believed it was worth doing. We thought the internet would be a very useful thing, that connectivity would solve a lot of problems. So we were trying to be as cost effective as we could without going broke. The volume charge model, we always talk a lot of crap about. People would say, oh, it's stunting the growth of the internet by charging for volume. Well, realistically, we had penetration rates that were among the highest in the world. And that was because we were charging the connection. It didn't cost you very much to have, relatively speaking, to have it at all. Okay, sure, yeah, if you wanted to use it a lot, it could get quite expensive, but it meant that we could get the internet out there and working. The university environment was a great place to work on this. We had people around the computer science department, other people around ITS, even things like the electronics facility or things like that were available to the university, though, were all very helpful. Universities are really interesting places to work. And we, in the early days, were kind of able to hide things under bigger budgets. Sort of put that under that rock over there. Netlink itself was successful because it was always focused on organisations, larger outfits, bigger budgets. And we stayed competitive even after the telcos moved into the market because we just weren't in the same space. They were selling dial-up primarily. They were sort of talking about other connections, but they were selling dial-up. And we held up, but it wasn't our focus. And that was where we were at. So, any questions? break time was. So.
Don, what was your most challenging time during this all the telecom history? What you want to share with us?
Sorry, say that again.
The most challenging time and most challenging stuff.
I don't know. They came thick and fast. I mean, a lot of things, you know, in any organisation or anything, the challenging things are quite often organisational stuff that have got nothing to do with the technology. You know, you're in an outfit that started off as a $250,000 turnover and it's now a $2 million turnover, and the staff numbers are going up and the scrutiny is changing, and, you know, they're that stuff, but that's true of every growing organisation. It's hard to say which were particularly challenging. It was a lot.
No Australians want to ask what the future's like?
Cool. Thank you much.
All right, thanks, Don. So next up, we've got Enable. We've got Mudasa, Brent, and Richard. I think you're all coming up. Come on up.
Thanks, Nathan, and thanks, Don, for that little trip down memory lane. At the risk of rebranding NZNOG as NZ Network Old Geezers, I was sort of thinking to myself, what was I doing in the post office in 1985? And I can recall installing some NEC TDM11s that were working at this massive speed of 300 baud. So yeah, I was part of the empire. I was part of that. Hold on to that revenue. Don't let it escape. Don't. Yeah. So I was part of the problem, Don. Also, just before I begin, I want to acknowledge the passing of a work colleague, Mike Taylor, last year. Mike was always, you know, one of his professional highlights was coming along to NZNOG. We all miss him dearly professionally, but also miss him, you know, for our regular coffee catch-ups at Espresso Studio. So anyway, here's to Mike. So I'm going to be kicking off just with a network transformation. I'm going to go pretty quickly through the first series of slides for a couple of reasons. One is that Mudasa took you folks through this, or a big part of it, at last year's NZNOG. And also, I figure that we should, you know, the more interesting bit is going to be a little bit later on with what Brent and Mudasa have got to say, so we'll get through the first bit pretty quickly. So the first bit of it is, you know, why did Enable want to go on this transformation journey? And fundamentally it comes down to we're running hard up against end of support with our vendor at the time, Huawei, and I'll come back to that in a minute. We're running out of network resources, and both logical and bandwidth related network resources. And this was the architecture of our good old legacy Huawei network. You can see there between the two EASs, we had 160 gig of capacity, and we were all sitting around sweating every time there was a fortnight upgrade would rattle through the internet, and we were getting up around 80-90% utilisation on that link at times. So that was one of the problems. The other thing is that it's GPON across the board. The uplinks from each of the OLTs, 20 gig, they were getting pretty busy as well. And so this is, we made the decision to put out an RFP. We went through this process with TFF at the time. And so this was, this was a 5-year program that we undertook back in 2021. And we ended up making a different choice of vendor. But this is what we've ended up with, a Cisco aggregation and a Nokia access network. I guess the key benefits are dramatically increased, an order of magnitude increase in terms of network capacity across the uplinks. We've got XGS-PON capability right across the network. And a whole bunch of other benefits that I won't go into. Now this migration program, as I say, it kicked off in 2021. We swapped out our aggregation network in 2023, had a couple of false starts, but finished that by November 2023. And we thought that was tricky, but little did we know what the access migration was going to hold for us. So we kicked that off in 2025. We're actually late 2024, but for the first half of 2025, we got the bulk of it migrated. We thought we were doing pretty well, and then we started getting some calls, and that's when it started getting really, really interesting. Now, I've listed 5 issues that if I listed all of the issues, it would be, well, we'd need the entire 2 days just to go through that. So I'm just going to really only pin or highlight one, which was internally we called it the Gen 1 Black ONT PON fragmentation. So our Generation 1 Black ONTs, they're roughly 13 years old. We thought we had the problems licked with interop with our new Nokia network. Turns out we didn't, and we had this one event back in May. And it resulted in 5.5 million minutes of downtime. 42% of our unplanned downtime for the year of 2025. And I guess I want to thank all those RSPs that are here for your patience. Yeah, we certainly caused you folks a few issues and problems. We made it into the media for all the wrong reasons. I mentioned that I wanted to keep this pretty short, and fundamentally this is all last year's news, so that's the main reason. So I talked before about what we've ended up with, this brand new network. It's always the technology group, what they do is they install something, commission it, stand up, and then they hand over to the operations team and say, there you go folks, you fill your boots, you operate it, which is fundamentally what I'm going to do now and hand over to Brent.
All right, I need to give a wee bit of background of me, actually, and Enable. I'm officially going to say I'm the new guy for the last time today. I started Enable pretty much midway through the Access project. I kind of knew I was in trouble a week before I started. I had set up a weekly catch-up with my boss. And the first week, we had a beer at the pub, and we talked about family, what we're doing on the weekend, that sort of stuff. Everything was good. The second week, beer at the pub, talked about family, a little bit about at work, what we're doing on the weekend. Everything was good. Third week, it was coffee, short, 15 minutes, done, out. Fourth week, I turned up, he said, no, I can't meet you today. We'll do it tomorrow. Turned up the next day, he said, can't do today, might have to do it tomorrow. He said, okay, look, we'll meet. We had a quick coffee, and he was just hands in head down, couldn't look at me in the eye, and said, we'll see you on Monday. I knew I was in trouble about then. So what I'm going to focus on, so two things in that. One, I'm probably the least technical person in this room, I would say. And two, Manasa set these slides up, so this is as much of a surprise to me as it is to you guys, so let's see how we go. So when I came in, what I saw and what I experienced was a bit of chaos, if I'm going to be honest. We were pretty open about it internally. We knew we were in trouble. We knew there was things going wrong, multiple things. We had a number that we knew of and were working through. We had a lot of people working in different silos. And I liked to call it, when I turned up, trying to stop everybody boarding the chaos bus. You know, when you're in a big storm, everybody goes either on the bus or off the bus, and that bus is being generally driven by anyone who's holding the purse strings, the financial guy. They probably shouldn't be driving that bus because they are just trying to run you around in circles as well. Our poor guys were just, you're at the end of your rope, weren't you, at that point in time. Richard, you know, you leaned on me pretty heavily, and we had a few whiskies and beers and just kind of got an understanding of what was going on. And then we started putting into place a methodology in order for us to go, what's the structure? What are we looking for? Who are we impacting here when we're doing these things? And how do we actually stop that? So primarily it was around these four things: the issue validation, the impact assessment and prioritisation, the clear ownership, that was the key one, and coordination, and then the stabilisation and cause investigation, which was tertiary to it, or last to it, because we needed to gain everybody's respect and confidence back that we could actually do these things. In order to do that, we needed to be controlled, predictable, transparent and progressive. We were all working in little silos. We had our RSPs working in silos saying, hey, you're getting this wrong, hey, you're getting this wrong. We had our engineers working in silos, just beavering away trying to get it fixed. We had the likes of our partners, Nokia and L2X, also joined in, and they were working in silos. And what we needed to do was change that internally inside of Enable. We admit we got a whole bunch of stuff wrong. We're quite open with that. We admit we broke things as we went. I think Don said it. You know, he was running to the next thing. Everything was, you know, such a rush to get to the next thing. You kind of let some things slip. To be fair, we let our processes slip. So we started bringing that back in. This is the one that we wanted to talk about, and Nathan was quite keen on this one when he said talk at NZNOG. So this was the fragmentation issue, and it was the hijinks between the ONTs and well, again, non-technical in the room, jumbo frames coming into our network, passing through and wedging up the queue there. So it filled the queue and it stopped PON ports from actually getting OMCI traffic to the ONTs. So what that in turn did was drop those ones off, and so we lost complete line cards. And it wasn't one, it was two, Richard. Or three. So by the time we got it sorted. And because it was so deep in the technology, it wasn't something that you could easily pinpoint, and it wasn't something that you could easily measure. We had our reporting and our analytics in place, but we didn't get down to that level. It wasn't until Nokia came to the party and went, in fact, I go a step back. It wasn't until we got Nokia in the room with L2X and the RSPs all together to go, this is what we see, this is what we see, and this is what we see, and was bringing everybody collaboratively together to go, okay, we see the problems, the multiple problems, but this is how we got through that one. So standard war room, not telling anyone in here anything different, but it was more of the human aspect than the technical aspect to go, who's looking at what, when? Okay, we do this. Who's looking at that now? Sort of, and getting that ownership of the problem. What ended up happening is that Nokia go, okay, we see what's happening here. We don't understand it. And went back to the R&D team, and they came back with a fix, which was an upgrade to the LT cards. And I'm going to embarrass two other people out here, because Shahid and Umir, who are sitting right up the back there, stand up. These are the two guys that basically rolled out the entire LT card. Mudasa helped as well. Don't worry about you. Out to the entire environment. So they saved us time, effort, money. They're champions. They're some of the best engineers we've worked with. So thank you, guys. So this was the collaboration that we were talking about. What we didn't have was communication between the partners in a meaningful way. Everyone working in silos, as we do, we're busy doing the things, but we didn't bring everybody together until a little bit later on, where we brought daily stand-ups to our RSPs in order to have those conversations. and to be open about them as well. Say, look, we know we've got trouble, we know we've got problems, what are you seeing? And your information that came back to us was probably the most helpful for us as well, because we didn't hold the layer 3 on endpoints, and you guys could see where the traffic was going, what it was doing, and how it was acting. There were some really good ones with Spark, where we were getting, different, same circuits, same services, different results. It didn't make sense, so there was some good learnings there as well. So it was our kumbaya moment inside of Enable to go, we're not doing this ourselves, and we're not doing this for ourselves. We're doing it for our RSPs, and they are doing it with us, not, we're not just delivering. I see you Diwali chaps down there. You were heavily involved as well. So, yeah, it's actually really good. I've never been to an NZNOG, but I'm looking around and going, I've sat in war rooms with all of you just about, which is good and bad, yeah. So we're really thankful for your assistance in that as well. Murray, I told you I'd name you, so yeah, thank you for those all. And those are now ongoing as well. So that's the thing, is it didn't stop. We kept those up so that if there are more issues, and there are always, we have that conduit. And you can come back to us and have that conversation, say, we're seeing this. So there was a real change in our work style there. Lessons learned. And you said it all earlier, like customers don't expect, they expect an outage. Like you're going to have them every now and again. It's how you deal with them, how you work through them, and how you resolve them in order to build the confidence back to say, hey, look, we're actually a really reputable network. We've actually got some really good things coming. Yes, we've made some mistakes, but we've fixed those mistakes, or we're moving through those mistakes together hand in hand with everyone else. I'm also going to whip through this now because I'm conscious that Madasta's got a lot to talk about, and he takes up all of our team meeting at the end. So I'm really helpful, I'm really thankful, I should say, to all of the RSPs that actually helped us out. It wasn't that we were doing it for you, it was that we were doing it together. I think that's the key message that I would actually say back to the environment that are here. So thank you. I think, Manasa, are we up to you? We are. So I'll pass over. Thank you, sir.
Thank you. So this was Richard and Brent who was talking about the past, and I will be explaining what we are doing currently. So my name is Mudassir Shahzad. I'm working as a lead network engineer in Enable. So I'm working in Enable from the start of the network transformation. We program, like Richard said, we started 5 years ago. So it was quite challenging and learning time for us to upgrade, which happens in 10 to 15 years of the network age. So we have been passed through this transformation program and have been a lot of learning. But still, like this work is still not finished. With the network upgrade and transformation and migration, our focus have been towards the, you can say, network stability. Like we have lost of customer impact in the last couple of years and disruption, so we want to have a more stable and optimized network. And also, like we traditionally, historically, we were working, our network was single vendor based, and we moved away from single vendor to multi-vendor environment, and which also brings a challenge for us. Previously, we have to manage network from a single network management system, but now we have 2 or 3 network management system, and that multi-vendor environment is challenging because historically we are not used to work in the multi-vendor environment, and also when we bring multi-vendor, 3-4 vendors, we also hit interoperability issues. Like you can see at the bottom is the network layer. We have access network on the left side from the Nokia, and in the middle we have aggregation and core network, traditional SD-WAN, leaf-spine architecture, and we also have building and facility management network, other switches. So there are 3 kind of different management systems. We are improving that we can build an integrated centralized network management system, so we can manage whole network at the central place. And when our NOC will be, we want to uplift our NOC capability to have the better centralized network monitoring and better response time and better incident management. So we are not only focusing on the monitoring and surveillance, we also focusing how to better monitor network traffic and performance, especially when we came to know the problem from the RSP side. We want to detect the problems at the early stage when they really, before causing impact to the customer. So same like we have multi-vendor environments, and we have to manage multiple systems. So we have network management system which can provide us the network insight and traffic, but we're deploying overall centralized Skylight SCDN system, which can integrate with multiple network management system, like we integrated it with the Nokia over Kafka, and we integrated with Cisco over telemetry, so it can provide us real-time and better traffic insights and traffic graphs, which is like giving us better capability to monitor and manage network. So we also have another initiative. We are upgrading, like Richard said, we after network transformation, our network is now XGS-PON capable. It means we can offer higher bandwidths to our customer on the hyperfiber, 2 gig, 4 gig, or 8 gig profiles. So we have the capable network, XGS and PON capable network. So we are upgrading from GPON to XGS-PON. So on the OLT side and LT card, this is already, but we have to do some field work. So like our SFPs are GPON, and we have to first upgrade from GPON to combo SFP. So combo SFP have built-in DWDM. There is GPON, XGS, and PON, different frequency wavelengths work within the same SFPs, and we can use the same fiber and same splitter. We don't need to change anything. And then also we need to change the ONT, because currently the ONT, majority of the ONTs are deployed are GPON ONTs. So we have to replace the ONT to XGS-PON ONT. That's another step. And we have already deployed Nokia first generation 240X ONT, but that have the limitation on the hyperfiber 3 services, and also have limitation on the higher data rate, especially at 8 gig profile. So we are deploying another new generation of Nokia ONT, which is 220X, and it can support hyperfiber 3 services, and also can support higher data rate like 8 gig. And also we at the same time, because GPON and XGS-PON can coexist on the same fiber, on the same OLT GPON card, so we are still deploying Huawei and Nokia GPON ONTs. So this is the capability showing of Nokia ONTs. So there are 10 gig interfaces ports on the hyperfiber XGS-PON ONT, and there is 2 ATA-wise ports, and similarly on the GPON ONTs, there are 4 1 gig interface and 2 ATA-wise ports. So this is our another initiative, which is network extension. So traditionally we were operating mainly in our coverage area in Christchurch, but now we are expanding to the remote areas to cover new development, new suburbs, remote cities. So we have our existing network, aggregation network. We just need to expand over the backhaul connectivity. We can have different model, like currently model we have a mix of access layer and aggregation switch. When we have a larger coverage area, we can multiple OLTs, and we can backhaul to our existing aggregation network. So we have 2 options here. Either we serve the customer traffic to the local RSPs, which are in the same area, like currently we're working in Nelson, or either we can backhaul the traffic to the Christchurch handover, existing handovers. It's dependent on RSP, how they want to go. There are both options available, but it's better if they use the existing handover into Christchurch, and there will be through tail extension, like they extend the service from remote areas like Nelson, other areas, over our tail extension service back to the Christchurch existing handovers. So when we did network transformation, at the same time we also have upgraded our OSS stack, because our previous OSS stack was built on the traditional protocols like SNMP and TL1 provisioning, because we were having Huawei U2000. But with the upgrade of our access network and aggregation to the new protocol stack, we upgraded our OSS, can support the new modern protocol stack. Like for the provisioning, we're using RESTful, RESTconf, intent-based networking, and also Kafka for alarm and even monitoring instead of SNMP, and also we're using RESTful APIs for automation and service orchestration. And on the this is on the northbound interface. On the southbound interface, of course, we have the technology has switched using from SNMP to NetConf model, which is more robust and modernized. So this slide is about our future roadmap. So as we have software-defined network at aggregation and access layer, so we want to leverage software-defined network capabilities, especially we want to manage network with a centralized controller. And another future roadmap is the testing trial for the SAP ONT. So currently we have two box solution where we install ONT and RJW, which is like not good customer experience. So we'll have SAP ONT, which can be inserted into the customer device directly, and a two box solution will convert it into one box. And similarly, because our network is 25G and 50G PON capable, because we have Altiplano, Nokia Altiplano, and latest software stack, we can support accept data rate at 25 and 50 G PON. So we will going to have trials with RSP soon. And we're also testing outdoor ONTs for the hardened environment and harsh outdoor environments. Currently, we have only indoor ONTs, so we are planning to test outdoor ONTs we can install on the poles, outdoor environment. And we're also working on the PoE extension. Currently, we have only 2 point of interconnects in Riccarton and Hornby, but we want to provide more locations in other central offices for resiliency and better availability. And the last is network expansion on our existing coverage. As the network growth is increasing, and extension to the remote area or to outside where we don't have coverage area. So this slide, the last slide, is about our, in the memory of our friend Mike Taylor, who was our good colleague and friend, and he have been a very active member of NZNOG. He been attending 3 NZNOG conference last time with me. So this is a picture from last year when we did an Napier. So we have just shocking news last year. His sudden death, and all the colleagues and friends were just shocked with news, and I just want to remember him for his all the time spent with us. He had such a good nature, and he was such a jolly person. I hope many of you know him, and that's all. And yeah.
So questions?
See, you should have asked earlier.
Was it realistic, 0 outages on the whole thing?
0 outages?
Yes.
Who said 0? I think you gave a number, didn't you?
There was 1 or 2.
Yeah. Oh, right.
Just interested in the, with hindsight, knowing what you know now, would you have gone with a multi-vendor solution?
Ooh, Richard.
Tricky response. Tricky question to respond to. Yeah. Okay. We'll go with the beer answer. The answer is no.
Yeah.
The complexity associated with, having one throat to choke when it comes to these sorts of issues. Brent was talking about it before. When we're dealing with some of these issues and having 2 vendors going, really tricky. We chose what we consider to be the best of breed of aggregation and access for what our requirements were at the time, and admittedly there's been a bit of a change of strategic direction in terms of where we want to go, what we want to do. So if we knew then what we know now, the answer would be no. We would have gone with one network vendor.
One quick question I have is, will you guys be around in the break and at dinner? I'm sure people will be interested in asking some more detailed technical questions.
Sure.
If you'll be around.
Yep.
so that you can give the beer answer.
Yep. Yep.
So I saw you flash up 2550 gig XGS PON up there. are you able to upgrade your 2x 100 gig links from your OLTs, or is that just swapping out the OLTs to do that?
So a combination of all of the above. So currently there's in by 100 gig capacity for our uplinks. We can get 800 gig out of those OLTs in the uplink direction. But we're also part of that 50 GPON trial that we'll be doing later on this year. That's a different OLT platform. It's the MF series. You've got 400 gig ports on those. So it's a combination of swapping out the platform, but also the existing platform can handle 25 GPON, no problem. Swap out of an optic and different CPE. Very good. Thank you.
Alrighty, thanks for that. Now we've got Murray from TFF talking about their migrations that they've been doing.
Hi, thanks. Sorry I'm a bit slower than some of the others, and Tuatahi are probably a bit slower working through the migration than Enable have been, but I suppose making sure that we do a good job of it. So which one of these? That one, yeah, cool. Looks like I might have the wrong glasses on here, so we'll see how we get on with using the slides. That's the button. Is that? Yep, cool. Okay, so I thought just before we start, I suppose there's probably quite a lot in common with the start of my presentation to the Enable one, in terms of the, we both have previously operated Huawei networks with a very similar architecture and things like that. I suppose the big difference for the Tuatahi network is that we've been much more geographically spread. So we've been operating a multi-region network from day one across the four regions. So the Hamilton or Waikato network, the Tauranga Bay of Plenty network, the Taranaki network, and then the Whanganui network. In our case, I suppose even within that we have had a number of COs, so which have ranged from building-based COs through to roadside cabinets that have enabled us to reach the smaller communities like the Ngārawahias and the Huntleys and the like of that. Each of the regions, so using those roadside cabinets, and they've been an important part of preparing for the access migrations and things as well, which I'll talk a little bit more about. Each of the regions has had a POI location or a handover location. In the cases of Hamilton and Tauranga, we've had 2 POI locations in each of those areas. Better take them off altogether. Yeah, so as Enable mentioned earlier, we combined forces through the process, RFP process, and then I think at the end of that, I think Tuatahi was fairly keen on going with a single vendor approach, and so we headed in a slightly different direction there. We also, at the same time as we were doing this, were thinking that we need to work through with our OSS and BSS systems, taking them to the next generation. I think initially it was intended that that'd be a completely separate project, but I think the reality is that just with the complexities and the interactions and things, that it had to be brought under the same program of work. The other thing I'll just mention very briefly here is that we actually have, I suppose, a fifth sort of region at the moment, which is our Hawke's Bay network. And so I'll talk about the other 4 regions first, and then I'll finish talking about the Hawke's Bay network at the end. So what we're changing, so through the RFP process, we decided to go with Adtran as our network vendor, or to partner to help to refresh the network. Also, because of the way that our network was structured, we've got all of our little regional towns and things that we had to provide backhaul for. So we've been operating a CWDM network initially, and that had to be upgraded as well to provide the additional capacity. So part of that process, we have been looking at rebuilding the backhaul networks that connect our smaller towns together. I think I mentioned that we've also taken on the OSS BSS project as part of that, and it ends up there's a huge amount of complexity and a lot of things that need to go right for things to move forward. So one of the things with the Adtran architecture is it's a disaggregated architecture. So rather than having a small number of large chassis, it tends to have a large number of much smaller sort of pizza boxes. I suppose that causes problems with building management networks. You've got to manage a whole lot more devices and things like that. So there are that's sort of one of the downfalls of it. But then it gives a lot more flexibility and things as well. The ONT strategy, with just the sheer number of ONTs and things out there, not possible to go and replace all of those as part of the refresh program, so needed to make those work. And I'll talk a bit more about the interop issues and things that we encountered along the way. And the black ONT that Enable talked about as an ONT that we also had in our fleet of ONTs as well, and that caused us quite a few problems. And so, but moving forward, as I mentioned briefly, we will be using the Adtran XGS ONTs moving forward for everything. So once our fleet of GPON ONTs runs out, then we'll be moving into using the Adtran ONTs. As a consequence of that, the technology we've used a combo PON technology. So I think we saw a nice slide of the coexistence of GPON and XGS PON on the same PON segments. In Adtran language, that's called combo PON, and we're deploying that exclusively across the network as we roll out with Adtran. I thought it was probably worth talking a little bit about the sort of migration architecture, because that's obviously a big part of trying to keep a network like this going. We can't just turn the whole thing off and then turn the new network on. There's got to be a migration strategy, and getting this right can have a huge impact on the process. So you can see there, Huawei network, much more abstracted diagram than the Enable one before, but made up of the same sort of building blocks. There's an access network and an aggregation network, essentially. So with the Adtran network, you have the leaf spine architecture instead. So the way that we sort of went through is we decided to migrate the aggregation layer first. And the way that we did that is to take the AES and then plug that into the Adtran leaves, and then move the RSP across onto that. And I suppose the nice thing about that is if we ever did need to roll back, then it was a relatively easy rollback process. We didn't actually need to touch the Huawei configuration at all to do that. It was just moving leads, moving patch cords across to enable that. maybe I can probably talk a little bit more about that process. You know, we did quite extensive testing through that, and while I suppose we found a lot of problems with MC lag and things like that, it's probably worth mentioning in our Huawei network, when we gave RSPs had lags in their handovers, that we would try and distribute them across multiple cards, so that when we moved to ADTRAN, we didn't have multiple cards in the chassis, so the only way that we could achieve that was to do multi-chassis lag. And it turns out multi-chassis lag is quite hard to get right. And so, you know, while we picked up a lot of problems with that in testing and things like that, and you know, there were, I suppose, a few delays getting some of those things right. You know, the migration process went relatively smoothly. I think there were a few rollbacks with some sort of lags not balancing properly and things like that, but they were resolved by the vendor pretty quickly, and then we were able to move forward and then move on and start thinking about the next phase, which was the access migration phase. So in that particular case, for the next phase, we went through, and then that was basically swapping over each of the PON segments from the Huawei aggregation and up through the full ADTRAN stack. And again, done in a way that, you know, the outage is basically the length of the time it takes to move a patch cord from one to the other, and time for things to settle down again. And then eventually, you know, the Huawei network ends up not being part of the network at all. So where are we at now? Aggregation migration was finished, I think, now probably a couple of years ago, I think it was. And all handovers are on ADTRAN. One of the things that this enabled is the 100 gig handovers. And towards the end of last year, I think, you know, there was a new 100 gig handover product released. And now we have done a number of the 100 gig migrations, so there are a number of RSPs now using that. One of the other things that has been enabled as part of that process is that we've never had a geodiverse handover product, and you know, with Hamilton and Tauranga having multiple POI locations, and with the move to ADTRAN, we have now got to the point where we've got geodiverse handovers, and we've got a number of RSPs that are now taking those up, and I think all working well. So from there, we've moved on to access migration, and as of the end of last year, I think we managed to complete the migration of Whanganui. So that's all now done, which has been a massive step. It wasn't all smooth sailing, which I'll talk a little bit more about shortly. This year we've now moved on to New Plymouth, and that's sort of now about 80%. The New Plymouth, the main, you know, the city centre, or the city of New Plymouth is now sitting about 80% complete. We've yet to, the next we'll be moving on to doing all of the smaller Taranaki towns. So those are all the ARC-based sites. And then once that's done, then we'll be moving through and doing Hamilton and Tauranga. We have I think we have a small number of customers in the Hamilton region that have been moved across to the ADTRAN network, and you know, things like the hyperfiber services, we're starting to use that across the entire network. So that's enabled that to happen more readily than it was previously able to. So I suppose in terms of the scale of the migrations now, we're sort of working through moving thousands of customers per week. So it's sort of getting more cookie cutter. I think there is probably still a little bit more refinement to go there to try and increase that number. But we're trying to get to the point that or targeting having the complete network migrated by the end of this year. Okay, so major challenges. I think with projects of this size and scale, there are going to be problems, and we've had our fair share along the way as well. And I think ONT interoperability has been a really major thing for us, as well as just being able to test things thoroughly before they make it into production. So I'll talk a bit about both of those. Interop reality. So we have a very large fleet of ONTs across, I think, about 4 different models, and they all behave differently. None of them are documented in terms of, it was a proprietary, it was a Huawei network, end to end. And so no documentation or no, ability to get support from Huawei to help to do that. So, this ended up requiring a large amount of reverse engineering and the likes to do that. And I think, Adtran have done a good job of doing that. Likewise, I suppose we had our black ONTs as well. I think these ONTs were sort of around the time that the PON standards were being finalised and things like that. So there are, potentially a few non-standard features and things in there that, in our case, I think we decided to go through and do a replacement program, and all of those black ONTs have been replaced to just ensure that they work. We don't continue to have problems with them. And I suppose the other problem with OMCI is that, as a standard, there are lots of extensions to that necessary to implement things like voice and the likes, and though they aren't standard, and different vendors do that in different ways, and so you've got to make all of those work. So I suppose the reality is that 85% of making it work is reasonably straightforward. And we did a proof of concept with the vendor earlier in the process, and that was all looking good. But then the final 15% is where all of the problems lie. So it's like the good old 80-20 rule, 80% of the achievement for 20% of the effort, and then to get that last 20% is actually 80%. But it was probably more like a 90-10 rule in this particular case. So as I said, although all of those Huawei ONTs are very similar, and they all have their subtle differences, and they all have to be accommodated in making them work through the interop process. So it has been taken a long time. Lab versus production. We have a fairly good ITF network, and in the Adtran case, because of the disaggregated architecture, we were sort of able to build for different environments, for the different levels of test, which we'd never been able to do with the chassis-based. It was too expensive to do that. So that's enabled us to be doing multiple sets of testing at a time. But I think the reality is that a number of things still make it out the other end into the production network, and that is despite all of the vendor testing, all of our own internal testing, RSPs coming in to do their testing as well. That we still had a number of problems come out the other end. And so I suppose to think about why some of that is, a significant or amount of it been is that we have no visibility of the RSP traffic. You know, we are just basically passing packets for them. And so, you know, issues with things like DHCP and that, we can't, although I suppose we're rewriting some packets or parts of packets and things as part of that process, we don't have any ability to tell what the state of those connections actually is. Also, just the scale and dimension, you know, in the lab, I think we ended up building a rack of a couple of hundred onts, but that's still very different to, you know, 20 or 30,000 onts within a region. And so there are, you know, scaling issues and things. You know, I know through certainly the aggregation part of the testing and things, you know, we were trying to simulate, you know, tens of thousands of connections. Okay, it looks like I need to move on a bit more quickly. Yeah, okay, so multicast issue, I suppose, you know, we did have a number of issues, and I suppose weren't aware of these issues until, again, the phone starts ringing and going, well, we've got connections that just keep dropping out. And you know, one of the issues that we found was the multicast replication. While multicast traffic based on S tag, so all traffic, multicast traffic on an S tag was replicated to the rest of the S tag, rather than doing that on the S tag, C tag, you know, because bitstream services are supposed to be point to point, not a broadcast service. What that caused was very confused CPE. So CPE would be getting, you know, connection status from other ONTs and not quite knowing how to deal with that. And then, yeah, so that caused us quite a lot of problem, and, you know, RSPs quite a lot of problem as well. Yeah, so in that case, you know, once we identified the problem, then we went through, we actually paused the migration. We worked quite extensively with our vendor to rectify that problem, and then once it was rectified, then started to move forward again. Yeah, so I suppose just, yeah, one of the key learnings coming out of this is just the importance of working with the RSPs through this process. We got to the point of, you know, having regular meetings, setting up Teams channels, and then, you know, pre and post every migration, checking in with the RSPs to make sure that things were happening as they were, and then, you know, working with them extensively through some of those problems to provide us data on the state of the connections, and that made a huge difference in terms of the resolution. Just having that extra data that we just didn't have the visibility of otherwise. So, yeah, I'd like to thank RSPs for all of their efforts and all the support to help us and you know, get us to the point that we're at now. Yeah, it certainly was not an easy time. And cool. Yeah, so I suppose in terms of how we might go ahead with this in the future, you know, obviously the testing, and the more testing we can do, the more we can reduce that gap between what's tested and what, you know, the number of errors that actually make it into production. So we're in the process of building a new ITF, and, you know, that should help with that quite a lot. Okay. Yeah. Okay. So just quickly to finish off the Hawke's Bay network, as you'll be aware, Tuatahi purchased the Unison Fibre network, I think at the start of 2025, and now sort of working under the Tuatahi banner. Yeah, so some of the things that we are doing there are to try and get that more integrated in with our new OSS and BSS system. So, you know, it's currently still working under the previous one. Another thing is to try and, is to move it. At the moment, that network is broken into essentially 3 regions. There's Napier, Hastings, Taupo and Rotorua. They all have their own sets of handovers, and we're working towards having it so that you can pick up those services. So Taupo service could be picked up in Napier. So the handover points will be Rotorua, Napier and Hastings for that, and you'll be able to pick up any service at any of those 3 handovers. As well as sort of working through a modernisation project, just so that we can do things like support 100 gig handovers that will be able to support things like XGS PON, and integrate into our OSS and BSS systems. So, you know, you should expect to see quite a lot of change in that network over the next 6-12 months, I think, as we work through that process. Okay, so I suppose, you know, looking forward, you know, for the next 6-12 months, obviously migration is going to be our primary focus on both networks actually, working through you know, the modernisation on both of those, and then yeah, hopefully, you know, look forward to you know, doing more exciting things as we move forward. Any questions?
Thanks, Murray. Just quickly, confirm you're going to have Unison equipment in your ITF that we can test to?
Correct. Yeah, we are just in the process of doing that now. Probably as we speak. I think the final switches are probably being brought into that network now. So we're that some of the testing you will have done up to now will have been done out of Hastings. We are now moving all of the ITF that ITF environments into our Hamilton-based office. Cool, thanks.
Alrighty, thanks for that. I think learning I got out of that was, you know, the collaboration between the LFCs and the RSPs is really important. So go and talk to these guys and build those relationships so that, you know, you can work with them in the future. And also thanks for Netcom for building a really good router that crashes after a whole bunch of multicast. It was really good for detecting things. Okay, we've got a break now, I think for 30 minutes. And we'll see you back here at 3:30.
All right, let's start. Final stretch for day 1. A few announcements for the event this afternoon. So buses are leaving at 5:30 from outside the entrance here at the bay. You can drop your bags at the hotel, or if you want to, you can leave them at the reception downstairs. For tomorrow, for those that are leaving, you can also leave your luggage at the reception downstairs. Another announcement for those that are yet to claim their Mercury iPhone. So the lucky numbers are 364 and 489. So check your bag, find out if you are the lucky winner of the remaining iPhone. So if you are, then there are the 2 persons, Karen Karen there. So any of those two, see them and you get a brand new Samsung iPhone. Right, for the session this afternoon, we are delighted to feature a lineup of speakers bringing in deep technical expertise and real-world experience across the NetOps data center as well as network automation. First one is Basim Al-Sabri. Not too sure whether that is the right pronunciation. Yeah. He will be presenting on NetOps with Open LLMs and RAG. So Basim is the founder and network automation lead at Netomate with over a decade of experience in networking and automation. His session will explore how OpenLLM combined with retrieval augmented generation can transform NetOps, enabling context-aware automation while maintaining data sovereignty. Over to you, Basim.
Good afternoon, everyone. Thanks for the introduction. My name is Basim Al-Sabri. I'm the founder of Netomate. We specialize in building network automation solutions for service providers and enterprise based out of Sydney. And today I'll be talking about network operations and how can we leverage AI in a safe and in a secure manner. And we'll try to keep it like away from the hype. I know it's a topic that has a lot of hype around it, so we'll try to keep it real and de-hype where possible. So we're going to have a look at current landscape of network operations and what are the issues that we're facing and against scaling. We're going to talk about retrieval augmented generation and see what it is, and how we couple that with open source LLMs to make AI available or AI capability available for our networks. We're going to talk about the architecture components and key decisions that we need to make in the solution. And then we're going to talk about some practical use cases and some challenges before ending with a summary. So I think it's been touched on in some of the talks that's been here before about the issues that network operations deal with, and that's you have plenty of logs, plenty of alarms, and a multi-vendor ecosystem that's really hard to troubleshoot, and it's very siloed, and that landscape keeps on and growing, and whereas the network operations team in general don't grow as much. And so what we see is in a fragmented network domain, sometimes it's really hard to, once issues arise, it takes time to reach a problem resolution or to kind of identify where the root cause of the problem is. There is a lot of manual investigation, and we also have network operations teams are generally overflown with tickets and repetitive tasks that need to be done, but no automation is available. And even in cases in which we have some sort of automation, conventional automation or traditional automation has a narrow scope of tackling problems, and it does take some time to implement. And it does not have reasoning capability the same as AI. So if we have a talk about what retrieval augmented generation, it's basically a technique or a framework that kind of allows us to ingest data into a large language model that it has not been trained on, and that's basically your data. So if we take a network operator, so that would include your knowledge base, that would include the network configurations, logs, alarms, ticketing system, and change management. And so there are two parts to it. The first part is the data ingestion layer, which is in the bottom right there. It starts with your data, and so that includes anything that you need in your day-to-day of operating your network. So your knowledge base, your configs, everything related to your network. So the first step, what we do in retrieval augmented generation is taking that data, breaking that into sizable chunks that then we can embed into a vector database. And so this step of like the embedding the chunks into a vector database, it's basically like a conversion from text to machine language, which is basically vectors and numbers, and then storing that in the vector database. And so if we take a normal user query to an LLM, by adding RAG, what we do is we use the same embedding model that we use to convert the data to that vector database, to use a semantic search. And so it's basically like a similarity search between what we're querying after. And then based on that, it kind of like retrieves the most relevant data to our query. So for example, if someone is asking what is the process to do like an OS upgrade, or who are the top talkers in the network, or what's causing congestion. And so if we've done the job of ingesting all the data there, then the LLM or RAG would come up with the closest context to what we're looking for. It would then add that context to our query, and then feed that into the LLM, and then that would give us like an answer that's relevant to what we're looking for. So why do we need RAG? I think the main thing for RAG is the ability to give a generic LLM context to be able to help us with our day-to-day operations. And so that way, as useful as using AI is, we can all agree that like you reach a stage in which like it would be really good if it actually knows your environment. And that's the capability that RAG gives us, without really having to go through the effort of like training a large language model, which requires a lot of like hardware and like a lot of investment. And this gives you the capability to have like reasoning within your environment that's based on your configs, based on your logs, and based on your knowledge base. And it's also been proven that like some studies have been done on retrieval augmented generation, and it actually helps in reducing hallucinations by 70 to 90%. It does not eliminate it completely, but that's still a good outcome. And then the other part of the solution is actually combining retrieval augmented generation with open source. And the main benefit of using like open source is actually it gives us access to AI or to LLMs in a private manner. So that way you still keep your data. You don't have to send it to a third-party provider, whether it's ChatGPT or whether it's Claude. You're able to download an open source LLM, and it's almost like as easy as downloading like a Python library or downloading any software. You just download it to your environment, and there you can feed your data to it. So you still have like complete control of where your data is. And so this, let's say if you start using like third-party vendors, then you start being charged by API calls, and every time you use large language models, you have to pay for that. This one, with this solution, once you download the large language model, you just have to pay for the environment that you have. So that's like the GPU, if you have it like in the cloud, or if you have it in your own environment, you only have that one-time cost of the infrastructure, but then you don't really have to pay for the LLM capability itself. And so this allows you to have like rapid innovation, or being able to adopt AI without having to wait for third-party vendors to come up with solutions how to enable that capability. So the core architecture components for this, the first part is the data layer. That's where it all starts. And it starts, like we mentioned, like your source data, so anything that would help you in investigating or in troubleshooting issues and in building your environment. The second part is chunking, is how do you break that data in a meaningful way. So if we're looking at documents, generally breaking them by paragraphs is a good way, because it keeps the context and breaks things into a sizable manner. And then embedding, which is converting that human language into machine language, and then storing that in a vector store or like a vector database. And so there are some open source solutions as well for database, and some of the current database vendors are actually even supporting vector databases as well. Chroma is one of the easiest ones to kind of like start with, and is generally good for proof of concepts. The second layer of this is the retrieval layer, and the most common and most basic is what's called top K retrieval, and that's like where you define a number K. So for example, if we take K to be 5, that means you, in terms of the search results that come to you, you select the top 5, and that's what you feed into your context. And so we want to be in a place in which we pick K that's large enough to get enough context, but then not large enough that it dilutes the context. So that's something that we kind of like need to tweak as we go. Hybrid search is kind of like where we combine semantic search with keyword search. So that way like you get the best of both worlds. And then re-ranking is like where you introduce a large language model. And what it does, it looks at the results that you have, and it kind of like reorganizes them to see if it has been missed like in the first run. So this has the ability to kind of like improve the accuracy, but it also adds some latency. Query rewriting, that's like where you also introduce another LLM to kind of like improve the prompt that's done by the user. I think we've all been in a place in which the more we use like AI, we become a bit lazy in terms of like what we write to it. I think it starts by you misspelling something, and then it still answers you correctly. And then with time, you just become lazy and lazy until you just like write random words. So query writing is a way by which we can have like an LLM take a look at the query, improve that, and then send that. But that also adds a bit of delay, and sometimes can actually deviate from the actual meaning. So the best solution to that is actually to write things properly, but this is a good mitigation. And then the last one is multi-source retrieval, and that's where we combine different data sources. So that can be like the knowledge base, the alerts, the network monitoring system, and that way we get like a more complete picture. In terms of the generation layer, the open source ecosystem for large language model is actually like very vibrant, and there are like a lot of good large language models that's being developed by different companies. So we have like Llama from Meta. We also even have GPT OSS that was released by OpenAI, which has the same capability as like an O4 Mini as per what they have advertised. So there are these different models, and then they come also like in different sizes and different capabilities, and that kind of like allows us to pick something that's like custom to our needs and based on our like hardware requirements. So for the larger models, they require like a lot of GPU. Some of the smaller models can actually be run on CPU without GPU, but just like with less capability. And then when it comes to inference engines, the two most common ones which kind of like allows us to run these models. The first one is OLLAMA, which is like an easy way of getting like an LLM to your machine. It's like 2 lines to like takes like less than 5 minutes to actually get like an open source language model into your machine and just being able to actually test with it. And then VLLM is kind of like more production grade and faster. And the saying is, you use OLLAMA to get from 0 to demo, and then use VLLM to get from demo to production grade. And the last layer in this is orchestration. And so that's where you have your workflow controller. This is how you put everything together. This is where you also add tool execution. So you have like either API calls to different systems, or you can even use your, if you have any existing automation workflows that can be used as well, and adding like multi-step reasoning. There are some, also like in the ecosystem, there are orchestration frameworks like LangChain and Lambda Index, which kind of like really help a lot with getting started with a lot of the problems that you, or a lot of the solutions that you can do. So it gives you like a good starting point. So some of the key decisions that we kind of like come across with the solution, I think the biggest one is the infrastructure, whether you host that on-prem or on cloud. And that's gonna depend on your privacy policy and whether you actually have cloud presence. But in general, a good thing to do is to actually start in the cloud if you have presence. That way you do like a proof of concept without having to invest, without having to do like the down payment of like a large investment when you haven't actually like really done a proof of concept for something that's new like AI. So that can be a good start, and then once you have a proof of concept, then you can actually make an investment to going on-prem, or you can actually choose the best of both worlds and go hybrid. The second part is the chunking strategy, and that's how you break your data sources, and that's gonna depend on the data sources that you're dealing with. Different data sources require different chunking strategies. So taking an example, a document, then generally breaking them by paragraphs is a good idea. If you're talking about logs or alerts, then there are different ways of doing it, or grouping them by devices, or by time scale. That could be also like another one. So it's just like one of those, and there is like a lot of tweaking that goes into this, and kind of like I try to avoid the word like fine tuning, because so that like it doesn't get mixed up with fine tuning, which is actually training a large language model. But there is like a lot of tweaking and evaluation that goes in this solution. Embedding model, the thing to keep in mind here is that there are some embedding models that are provided by OpenAI, by Google as well. But the thing that you need to keep in mind with this one is like if you choose to go with those, then you're actually sending your data elsewhere, and that kind of like beats the purpose if your goal is actually to keep your data private. So there are some embedding models that are local, and so just keep in mind to not use like external party embedding models. If you're going for a open source large language model, it kind of beats the purpose to use like an embedding model that's that kind of like sends your data outside. And another note here is the embedding model does not really have to be like the same from the same provider that gives you the large language model. There are like two different pieces in this solution. One of the important things as well is like the model selection, and there are a few factors that goes into it. Different models are strong in different areas, so some of them are strong in coding, some of them are strong in classification. They also come like in different parameter sizes, and that dictates the hardware requirements, that dictates also the accuracy, and yeah, dictates like the speed that you get the results. So also there is like a bit of trial here to see which models are good for which workflows, and certain workflows would have different requirements. Inference engine, very likely like Olama is a good starting point that gives you like a quick way to do like a proof of concept. And then you move on to VLLM once you're ready for a production grade solution. And then we have Llama CPP, which is good for very constrained hardware requirements, like having the edge or just like not having strong hardware capability. And then the last thing is quantization, and you can just think of it as compression. It's a way by which to you can compress the large language model, and by doing that, you also reduce the requirement for the hardware requirement. So generally, the parameters are generally stored in 16 bits, and reducing to 8 bits greatly reduces the requirements, but also it's not too lossy. So it's a good kind of like compromise depending on your hardware requirement. And then you also can go to 4-bit, which really further reduces the hardware requirements, but then introduces a bit of loss, as with any compression algorithm. So some of the practical cases, and I think the major one is the ability to actually speak with your network in your language and not having to know the commands to deal with the network. So that kind of like really empower network engineers with, let's say, having to adopt like a new networking vendor, so you don't have to go through that initial bridge of having to learn the command line. You have like this common language that kind of like allows it. It also democratizes the network, because when you have this layer, then you can have non-technical folks as well being able to actually talk to the network. So that would include like project managers and managers being able to query things quickly, not having to go through network engineers in some cases. Yeah, and one of the benefits is, well, you can actually introduce like an event-driven incident triage. So like when you have your tickets, you have like an automatically AI go and summarize it and have a look at the network as well, and try to come up with potential solutions. The thing to note here is, so far in all the implementation, all of the work that I've done, we've only been focusing on read-only, and we haven't given AI access to production. So that's an important thing to keep in mind. So it's really good for read-only operations and like assisting in solving or kind of like guiding you through issues, kind of like in a best effort way to say, hey, looking at all your network, looking at your logs, this is like what I think the problem is, and then it kind of like needs to be kind of like validated by engineer and taken and actioning the steps. The last one is like knowledge retention, and this is something that I use a lot, like with an agent that I'm using, is because most of my work now is being done through an agent, whether it's like coding, updating tickets, and so this gives a really good way to say, after I've done the work, to say like, go and update the ticket with what we've done. So it really simplifies like knowledge retention or updating the knowledge base as well. So it gives you like a way of doing that automatically without having to do that in a manual way, moving tickets from like in progress to done and all that. So some of the challenges that comes with it is like, this is not like a turnkey product. This is not something that's like available that you just like purchase and then this is something that you have to build, or you build it with a partner, and it's based on your environment and based on your data. Like hallucinations are reduced, but they're not completely eliminated. And I think one of the important things to add to this point is a good workaround is to always have like the sources listed, and that way like you can always validate if what's being said is true or not. And one of the points is that as good as open source large language models are, they're still lag behind the frontier models. It's depending on which benchmark you're looking at. It can be 3 months and it can be 12 months, depending on the benchmark. And so, but then having open source large language models there, coupled with RAG, really just like improves the value that you get from them. So even though they're a little bit behind, but like if you couple that with RAG and being able to identify with your network, that really simplifies things. And some AI capability, I think, is better than no AI capability. And the last point is like that the skill set is still emerging. This is like a new technology. The industry is still trying to figure out how to like leverage it in a safe manner. And so it kind of like does span, especially like if you implement it in networking, you need the subject matter expertise of network engineers, software engineers, and then AI engineers. The only thing is like you don't really need to be like an AI scientist to apply it, but you just need enough software skills to kind of like implement the solution and just be familiar with the lingo and with all the technology that comes with it. But it's not like, you don't need to be like an AI scientist to implement this solution. So the key takeaways is like RAG combined with open source LLMs make it like viable for us to kind of like start experimenting and start thinking about how to incorporate AI into our networks and like help us in our day-to-day operations. The second point is the jargon is scarier than the work. Like for someone coming from a networking background and let's say looking at all these terms, there seems to be like a lot of keywords, a lot of technologies, a lot of frameworks. But in terms of like application, it's not super difficult. I would say it kind of would probably be like simpler than going for the CCIA in terms of like the skill set. Like a lot of it is, some of the work has been done, some of it just like you just import libraries, you really don't have to, like go through a lot of effort to implement it, but you need to do some work to get there. And I think this is also like an important one, is that it augments and does not replace what we do. And I think that's also like one of the issues with the marketing around AI, is like there is like a lot of hype around AI, and it can do like everything. And there is like a recent study by MIT that says like 95% of AI projects like don't scale or are not successful. And I think one of the main reasons there is the high expectations, and it's like not realistic expectations from AI. Because as good as the technology is, it's still not reliable to operate by its own. It still needs oversight. It needs double checking by engineers. But it does a good way of summarizing or taking the grunt work out of a lot of the things that we do. And then, it's like I said, it's an early stage for AI, but it's at a place in which we can actually start using it and start experimenting and start deploying it. And the last point I want to bring is like that AI, and I say the same thing about like network automation. It's not like something that you implement once and you're done with. It's something that you implement, it's a capability, and then if you want to get more of it, you need to kind of like invest more into it to kind of like enable that capability. Thank you.
Good. Time for one question.
Right, next speaker is Tim Raphael. So Tim is the regional product line manager for IP automation at Nokia, with extensive experience in designing and operating large-scale networks. So his talk is about evolution of network configuration management, and he'll be covering how we went from manual approaches to modern intent-based API-driven. Over to you, Tim.
That glass was definitely going to fall off the table. All right. Good afternoon, everyone. Thank you for the introduction. My name's Tim. I cover the network automation product suite at Nokia for APAC. So I have two products, but they're not what I'm going to talk about today. I'm here to talk about the evolution of network configuration management. So I've had a lot of fun putting together this talk because I got to dive into some of the history of how networks were operated well before my time. So some of the talks from this morning were very, very interesting to me. So in the beginning, this was part of the fun. Binaries, buffers, and text files. So my understanding is early devices typed configuration directly into them, and it wasn't configuration as such. It was loading into text files and rebooting, or just even without persistent storage, you were loading into runtime memory. This is the era of systems engineers, not network engineers, as we are today. Routers were computers, computers were routers, until we got to the FPGA ASIC sort of dedicated forwarding side of things. So it was a very different mode of operating the network. You were effectively stringing computers together. In my investigations and research, I came across this, RFC 789. This is from July 1980, and it describes what I believe to be one of the earliest public outage reports from early ARPANET. So go and have a read of this RFC. It's not an RFC as such. It was published before the RFC standards were brought about, but it basically details a routing protocol runaway in early ARPANET, causing a systemic crash across the whole network. The conclusion from this RFC was, we need a way to be able to remotely manage and configure the devices in the network. So this, I feel, is one of the earlier publications that talks about remote network management and configuration protocols. So please go have a read of this. It's a fantastic read, unlike some of the dry RFCs that come out nowadays. So, management protocols. Where did we start? So, following that early 80s publication, we ended up with the late 80s where we're getting SGMP, HEMP, and CIMP. Now, these protocols set to address some of those shortcomings of the early devices. SGMP, for example, just had a very simple set and get mechanism where you could ask for the configuration or the state value from a device, or you could set that value. HEMP, or High Level Entity Management Protocol, went the next step further and allowed the device to send an unsolicited notification from the device to indicate that something had changed. It sounds an awful lot like an SNMP trap. And then we had CMIP, which was based on the ISO line protocol. So rather than IP, it was over ISO. So these built sort of the origins of SNMP. So we ended up with SNMP as a conglomeration of these protocols where we had traps for notifying and sets and gets. We also then started to look at how to structure the information that you're querying or setting. So different vendors doing different things, configuration being stored differently in the device. We came to build the idea of a management information base, or a MIB. So this lays out the configuration or the state information in the box and gives you a number addressable path, if you want to call it that, to access it. Obviously, this had some shortcomings. If you look at it from a modern lens, it was relatively slow. Required multiple CPU cycles to set and get, and particularly to gather information periodically. But what we ended up with was the start of a descriptor language for the state and configuration of a device. So then we moved towards the era of the CLI. So interestingly, SNMP and remote management of these devices came first. So unsurprisingly, a lot of the CLI that we ended up with was based on SNMP. So even in Nokia's SROS, based on the Timetra TMOS, the configuration syntax, even still today, follows some of the MIB paths. So if you use classic mode on SROS, you might be familiar with setting some of the Nokia Timetra MIB paths. It was just a natural progression to go from that information base to something that you could synchronously interact with. Others took a different approach. Cisco was originally pulling config from TFTP, but then they came up with the industry standard CLI sometime after to start to abstract that process. Also, this was the departure from pushing configuration into buffers and files and actually doing something interactive where there was, you enter a command, you hit enter, it validates and it applies all in one go. And so, you'd have dynamic update to protocols and things like that. You didn't require a router to be rebooted to apply. And of course, once we had CLIs and we had humans creating CLI scripts and CLI configuration, we then decided to automate that by preparing changes and screen scraping from the router to turn that into something that you can build. So TCL, or tool command language, was originally created in the late 80s as sort of a string typed processor parser, I guess, but then it was extended with expect. So this is the capability that I'm assuming a few of you have used in the room, where you have it look for the router prompt and it waits until it sees the login prompt and you put in the username and then put in the password and then you wait for the brackets and the hash and then you go and push your configuration in. I suspect through the 90s and the 2000s, so much provisioning was done with TCL and expect. So much of it. But we had to evolve, right? We had to move on. And the era of APIs, although I could have made this section 10 times as long because every vendor came up with their own different API, but we had to sort of come towards an agreement on where we're going with these. So I'll start with the obvious. I'll skip over the Juniper specifics and the Nokia specifics and all the different HTTP variations that came about. But NetConf probably sits in terms of, where everyone settled. This ends up being about the average. NetConf was a standards, or is a standards-based XML RPC API. So by RPC, I mean remote procedure call. So I call a method on the router and it executes something and it returns something. Seems like a fairly, simple definition, but this is what drives a lot of modern automation and modern microservice interaction. In terms of NetConf, XML-based, but JSON was added later. This could operate over Clear Channel, or more commonly nowadays over SSH, and you get replies and unsolicited responses through an open channel. A bit later on, we addressed the concept of the data storage. So as I said, SNP and MIBs. Now we're starting to talk, much larger responses with much, more structured requests and replies. We needed a good way to document those because vendors were doing different things, but they were all sort of converging on the same concepts of different configuration databases, get and sets, and they were, working around this NetConf standard. So to make things a bit easier, in 2010, this Yang thing came about. And anyone who's, tried to look at a Yang model, you'll understand that it's human readable. It builds a tree of modules and containers and lists and leafs, and it's a data descriptor language. So similar to an SNP MIB, but it's much more flexible, and it allows you to distinguish types and data storage in terms of lists or dictionaries, and it builds a much better way of describing languages, or describing data, should I say. The benefit of Yang is you can take a Yang model and turn that into bindings for your language of choice. So you can turn it into Python bindings or into C bindings, C++, anything you like. And you now have a way of programmatically accessing the data without having to manually build it yourself. It's all derivative. We also ended up with OpenConfig. So this is a standard set of Yang models that describes internal state and configuration of devices. So taking this RPC idea one step further, we can thank Google for this one. That's what the G stands for. Open sourced in 2015, the gRPC standard. This is doing RPCs using protocol buffers over HTTP effectively. So protobufs, for anyone who's not used them, it's a wire data format. Again, you describe it in a protobuf file. You determine, the type, the length, similar to what we do with, packet frames today, except it's a wire format for an RPC. There's several different mechanisms. You can have unicast streaming, bidirectional streaming, request set. You can have all sorts of directionality with gRPC. But this is the way in which Google designed their microservices clouds. So they'd all do gRPC between one another to, trigger mechanisms and sync state. But that came, the mic back, there we do. So that came to the network. And in terms of the network, it came to, it's over HTTP, which means it can be over TLS as well. So it's all HTTP streamed or HTTP request response. In terms of standardization, we ended up with some standardized gRPC interfaces, which I'll get to in a minute. So OpenConfig I mentioned previously. This is just a standardization of the Yang models, which can also be then applied to gRPC. So in terms of the various gRPC standards, if you like, so these are defined in Yang models. So the methods and the response and the replies are standardized, which a lot of vendors have adopted, including Nokia. So GNMI is the one you're probably most familiar with. This is for configuration, set and get, and streaming telemetry. So you can inspect the state of a configuration point, but you can also subscribe to changes. So when the counter on that interface changes, let me know. So every time that counter increments, you'll get a packet back. GNOI is also super appropriate for network operators. So these allow you to do operational commands against a box. Not typically configuration, but things like make sure this file is in this place, reboot the device, factory reset it, or run a tools command, be it a ping or a trace route. Two less frequently known, GRIBI, which I believe people have spoken about at conferences before, mostly applicable for very large networks that want to do their own programming. This allows basically direct fib manipulation. So match on packet, do action. And lastly, GNSI. This is probably the most recent of this set, but it's for security purposes. So nowadays, when we're talking to boxes over gRPC, it's all certificate-based. This set of RPCs allows you to set, rotate, and deprecate certificates and other authentication mechanisms against a box. So if you need to change the TLS certificate or SSH keys, there are RPCs in GNSI to help you do that in a standard way. So you might be asking, where am I going with this? We've got an evolution of configuring devices from writing text by hand that turns into configuration. Now we've got all these lovely standard RPCs that lets us do anything we need on the network. Well, there's been another sort of change over time as well. We started with imperative. So this is do this, then this, then this, then this. So it focuses on how you get to the result. It's the journey. It's effectively modeled on the user experience of the operator. Someone would sit down, they'd log into a router, the username prompt would come up. They'd put in the username, the password prompt would come up, they'd put in the password. And so we built automation to do the same. But what we really want is just say, make me a sandwich. I don't care how you do it, I just want a sandwich. That is the declarative approach. That's where you say, I want this thing to be in this state, and I don't care how you get there. I mean, you usually somewhat care, because you don't want to nuke the box and then put the config on it and have an outage while you do it. But you want to define the end goal. This is important because, this approach has enabled us to use platforms that are typical for systems. So I mentioned here, Puppet, Salt, and Terraform, for example. They are all declarative based. So you define the result you want, and the platform gets you there. The reason this is appropriate to modern networks is because the complexity has just skyrocketed. We were building fairly simple networks, then slightly more complex networks. Now we've got overlays and underlays, we've got TE, we've got LSPs, and now we're building AI data centers that are enormously huge with complex queues, complex timing, with complex job and scheduling mechanisms. This is difficult to manage as an operator. With a declarative approach, we can define levels of abstraction. We can build the functionality and the logic into those abstractions so that as an operator, I can say, go build me a new pod. And that information is known. That abstraction is done, and a pod to you has a given definition. We can call these definitions, if you like, intents. So is this idea new? Not really. Unfortunately, us in the network world have been sort of sitting behind some other operators in this space. Realistically, cloud operators, platform operators, system administrators have been doing declarative approaches for years and years. Take Kubernetes, for example. For anyone who's used Kubernetes understands the operator pattern. This is where you define a resource and you give that resource to the Kubernetes API. That resource will trigger an operator, and that operator goes and makes that resource a thing. Because Kubernetes is generic. It could be anything. You could tell Kubernetes, I want you to make me a brewery. And it has an operator that calls a builder and builds a blueprint and orders the infrastructure, and your brewery gets built. It's generic enough that that could be the case. Except we use it for storage and pods and other smaller things. So then why don't we define these resources for network abstractions? Well, there's a few issues here. For the network, we like to do things atomically. So most of us are used to using a commit-based network OS, where you make your changes, you check the diff, and then you commit it, and it applies in one go. Kubernetes is not like that. You apply the resource, and it will go and try and create a pod on a server, for example. But if that server has no capacity or the storage is full, it will sit there pending. And you have to go in as an operator, and you have to go and free up some storage, and then it will come good. As an operator, if we're doing this on the network, we want our change to succeed, or we want it to roll back. So there's some orchestration needed there to make atomic commits and transactional commits across the network work how we expect them to. It's also key that we know the state of the network at any given time. You don't really want to apply an import policy change on, say, 10 routers and have it succeed on 8 and fail on 2. That's just an outage waiting to happen. Ideally, it works on all of them, or it doesn't work at all. So there are solutions for these things, but that's not what I'm here for today. So looking at the benefits of this approach, rather than, say, the negatives for networks, well, infrastructure as code is an obvious one. It allows you to define exactly what you want and the exact state of the network at any point in time. You have the benefit of Git, so you can version control. You can roll back, you can review, you can see the difference. And the infrastructure as code ecosystem, because they're running ahead of us, there's already a huge ecosystem of tools in terms of change tracking, change authoring, CI/CD, and testing infrastructure. So what does this mean for operators in a modern context? If we start embracing infrastructure as code and declarative operations, well, it means we're not CLI jockeys anymore. We're building complex networks. It's really difficult nowadays to take a modern PE router or a modern edge router or a modern DC fabric and configure it by hand. There's a lot to do and there's a lot to understand. You're much better off using an architectural design you've built, template it, and then apply it everywhere. You improve the reliability of your changes by doing this, because you build it once, you build the concept once, and you abstract it, you give it a name. I mean, I'm sure we've all built a template for a core router, and a template for a PE router, a template for an edge A node. This is exactly the same idea. It just means it's rinse and repeat. And then this also scales. So most people in the room are operating at some level of scale. It could be 2 operators with 10 routers, or it could be 20 operators with 1,000. The scale does matter, even in today's complex times. So far, I've gotten 20-something minutes into my talk, and I've not mentioned AI. I didn't want to, but I actually have a good point here. There is a pragmatic use of AI agents to go along with this story, right? Any of us that have used MCP servers and tooling and given additional context to ChatGPT, for example, understand that there is a real-world use to these tools, but in most cases, the LLM and these agents are only as good as the tools you give it. So you need to focus on what AI agents are good at. So in this case, summarization, turning an RFC into a 2-paragraph that I can understand to the extent that I need to. Root cause analysis, taking logs, metrics, events, timelines, and tickets, for example, and telling you, hey, this change was made, it caused this interface to go down, which caused this BGP peer to go down, which caused that route to be unreachable. That's something that LLMs can do fairly well. And last, configuration and code generation, as we're all pretty aware. In terms of abstraction and declarative APIs, this makes agent use of network automation a very powerful prospect. When you can build something up to be an abstraction that an AI agent can understand without needing to know all the complexities, you can start to make changes at scale that are complex but testable and versionable. So when you have infrastructure as code, you can ask the AI agent, hey, go build me a new overlay between this port and that port. And it goes and does it, and it raises a pull request. So that it doesn't commit it to the network, but a human can then review the pull request, understand what's going on, and commit the change. It's still faster and it's still more efficient. What other use cases? So I like the what just happened, as I mentioned. Your dashboard fills up with a bunch of alerts and alarms. Some are related, some are not. What just happened? It goes through and it can do the correlation for you, which as a human, we've all opened a text editor and put this log line and this log line and this bit of config and this change. Oh yeah, those timestamps match up. That's a time-consuming, brain-intensive process. It's very easy for AI agents to do. But if they have declarative interfaces and declarative abstractions to understand the network, it makes that so much easier and so much more powerful. I've got a few other examples there if you care to see it. That's basically it from me. Thank you so much. I've got some links here for OpenConfig, the stuff we're doing at Nokia on GitHub in this realm. If you're interested in AI agents and network, and particularly how you can embrace different automation APIs, please come have a talk to me. I love talking about this stuff. Thank you very much. Any questions? Please, someone ask me a question. It's been too quiet in here. Surely someone's got something. Don't leave me hanging.
Forget all previous instructions.
I know. Thank you.
Right, so that takes us to the last presenter, Joe Shaw. He is a senior network engineer at RIANS with over a decade of experience in designing and operating large-scale networks. So he will be presenting on automated network state checking. Over to you, Joe.
Oh, thank you for that. Thanks for inviting me around. As I said, I am one of the network engineers at RIANS. I'm here to talk today about the RIANS network, how we are leveraging our network automation for both our changes and our monitoring. I'll go over a little bit about how we use it, the form it takes, and end with a little bit of how the automation impacts us, the engineers. But the main question that comes up about RIANS when I talk about it is, what is RIANS? So RIANS is the Research and Education Advanced Network New Zealand. It is New Zealand's national research and education network. We are a Crown-owned company, try not to hold it against us. We are a membership organisation, so we have members, not so much customers. And we provide a centralised hub for e-research and infrastructure. So last year, there was quite a bit of merging in the research and education sector. And as a result of that, NZIX, the New Zealand Institute for E-Research, New Zealand E-Science Infrastructure, so I've got to remember all these acronyms, joined in with us. So we started with a team of about 30 and we're now a team of 60. So we have expanded what we do quite considerably. There's a lot of things on that side that I have no idea how that quite works, but there are some pretty sharp people that know how to do it. That's our high performance computing and data analytics. It has expanded what else that we do. Naturally, I'm on the network and network protection side. We also do federated identity. That's how researchers can share their data and know exactly who is accessing it and who's not allowed to access it. And the NZIX folks also do the training and consultations to help you work on your code to make it work on these supercomputers. We are a member of the GREN, the global research and education network. So we are uniquely placed to bring these internationally developed solutions into the local market. The GREN looks a little bit like this. We just hang off the edge of it. Most of these links you probably already know, it's just the same submarine links. There are about 120 NRENs, and we're more collaborative than competitive. We all have our own little turfs and we don't really step on each other's toes. We just want to work together. We leverage these global relationships to connect our colleagues, the data and research people, to data and research people all around the world, and so that they can work on their global science initiatives. Our members, these are a good chunk of them. It has changed recently, particularly with the PROs, the public research organisations that were things like Ag Research or GNS, and now go by as sciences or bioeconomy, depending on where they're from. They could be universities. Some of them are just independent research organisations. Otherwise, it could be polytechs or Wananga. There are some new members from Canterbury, the Bragato Institute, which comes from New Zealand wine growers, and the ARA Institute, what used to be Christchurch Polytechnic, where I started my networking journey quite a while ago. So our members do come from both private and public sectors, but the main thing about them is that the research and innovation or education. So moving on to the network itself, I just need to say where we started from. So in 2006, the CAREN network was created, Kiwi Advanced Research and Education Network. Fortunately, around 2013, it was renamed to RIANS, before CAREN took on a different meaning. So we're going to stick with RIANS for the rest of the talk. And about 2008, this is what the network looks like. This is October 1st. This is a ring switching network, and there's only NREN connectivity. We can't provide you with commodity internet. If you want that, you're going to have to go to a commercial provider. It was built on, and I'm told, extreme purple packet eaters. Now, this is before my time, so I didn't quite understand that. It doesn't sound like they do very well. Fast forward to 2013, RIANS enters a joint operating agreement with FX Networks, who is no longer with us. Part of that agreement allows RIANS to start selling commodity internet alongside our other services, which makes a lot of sense when you think about it. And the network started looking a bit like this. So this is 2013. It is still a switching-based network, and it's sitting on brocades at this time. Moving forward to 2018, we've moved on from our brocades, and we're moved on to mostly a Juniper shop. MX480s and 80s, and maybe some EX switches towards the edge. It looks a bit like this. Now, by this time, we have entered the big boys. We've got MPLS under the hood now. We're not using Ether switch. We probably would have blown up our network if we were still trying to use that. A more significant milestone in 2022, I get hired at RIANS. At the same time, we have gone RFP for our domestic core network hard refresh. After quite some time and due diligence, this is public sector, so things take a little longer. We begin our deployment in mid-2024, and we finish the rollout in June of 2025. So only just last year. And today's network looks like this. We can see our ladder topology on both the weather map on the left-hand side and the indicative geographical one on the right. The ladder topology is from Auckland to Dunedin. It is 100 gig on both sides. That is somewhat recent. The last leg was just done the last few weeks ago between Dunedin and Christchurch, going via Wanaka and Invercargill to avoid the east coast of the South Island. Intercity links provided sitting on Eon Fibre Optical, so we're thankful for our partners there. For our international links, RIANS was a anchor tenant on the Hawaii cable system, which went live in 2018, and we have resiliency on the TGA. I'll note that fibre cuts are happening more frequently, and they can end up taking days to repair. There's an example of that last year when two fibre cuts happened within several days of each other. And some of you will probably be aware of what happened there. Some of these causes we know are likely to increase in frequency because they're tied to climate change. And some of them, like earthquakes, New Zealand's already pretty aware of what areas to be careful of. To avoid some of this, you will notice we've added other links, say from South Island, the Hawaii cable going up to Westport to Nelson, then Nelson taking the Spark cable up to Levin and on to Hamilton. This is to avoid both Christchurch and specifically Wellington. That's 3 pops there that are within 10 k's of each other. It's a bit of a risk for that particular city, so we want to make sure that if there was some sort of critical problem, the South Island, particularly me, is still connected. And we're probably seeing these days there are other risk factors to come in, such as geopolitical, which seems to be becoming a bit more interesting. And we're also looking to improve some resiliency between Auckland and Hamilton. So that's coming up soon, so I hope we'll announce more on that later. I prefer to look at the weather map in dark mode. I think it looks a lot sharper in there. If you want to have a look at what it looks like at this moment, that QR code will take you there. We automatically take snapshots every few minutes of the weather map over the course of a day. We package it up as a GIF. And the reason I was able to show you those is that we have every day the GIF for it all the way back to 2008. You can go to a website and have a look at all of them, and you can also see the progression of our network in that time. You might have known that that weather map that was up there originally was the PHP weather map, which is a little bit old in the tooth, long in the tooth now. We saw that and decided we would make our own. So one of our software engineers made the Raumata network map renderer. It's available on GitHub, it's open source, you can help yourself to it. We'd be more than happy to hear more about that if you want to use it and if you have any issues with it. So if you'd like to give that a go. I mentioned we went RFP for new hardware in 2022. This is the sort of hardware that we were going from and to. So mostly MX80s, chassis systems and POPs, with EXs sometimes for port fan out. That mix of edge does complicate network automation, as you sort of need to account for the VLANs hanging off a switch and what port. Now that there's 2 units for every service, it complicates a few things there. And we expanded out to using the MX304, the 204, the ACX 7100, and the ACX 7024. But we had made a problem for ourselves. We went for a network that was 20 to 30 nodes, and now we're going to a network that's about 80. We have a full mesh MPLS network with a full mesh of IBGP. That makes a fair bit of config and brings up the small matter of scale. The idea of manually writing all that config might make me reconsider my career choice. So we certainly need to either automate that or re-architect it. Because we're changing the hardware, we're a bit loath to change the architecture at the same time. Sometimes you have to, sometimes you don't need to, but we were able to avoid it in this case. Between 2006 and 2014, there basically is no automation. You do everything by hand. It's lovingly crafted by our network artisans. The problem with that is that even if it's crafted like that, it can explode because every engineer will do it slightly differently to everybody else, slightly bespoke. Even though if they come out with the same outcome, there are heaps of ways to do it. And that complicates parsing the network because every engineer did it differently. Between 2014 and 2019, we start making individual scripts to deal with specific problems, like the mesh problem. That's the major one that we needed to be able to deal with, not only to generate all the config required, but to validate that the mesh is still intact as people make changes throughout the day. You need to have another system checking your config that it's still actually achieving the outcome that you wanted. Each use case, its own script, means it has its own parser. Each script is contained. It has to go and collect its own information, figure out how to turn that into config, and do it all by itself. There's a lot of duplication here. All these different scripts might be scraping the same information, but they're all doing it in their own slightly different way. This starts becoming a lot harder to maintain, and you're, again, just doubling up your costs. In the same way, they have to also call out to our IPAM, maybe to pull prefixes. Each one does it in its own different way. Again, just making it more complicated. And so we get to between 2019 and the present. We wanted a network automation framework to unify our parsing into a single reusable model. So you're only building one giant parser, and all of your tools will use the common parser with the common network state sitting on it. Once we had a workable network parser, we quickly saw the inconsistent style of the current engineers and a lot of former engineers and the works of art that they'd left behind. Once the scripts are using that common parser, we modified the scripts to start using more common libraries so that if they're doing similar functions, just slap them together so that they're using the same library. You're not having to double up again. We decided to go with the Future Armor naming convention, and we named the framework Bender. Bender is great. Now, I didn't know what a monorepo was when I was told about it, so I had to look it up. Made sense for it. It's just a repository containing everything. It does help with the ease of code, to reuse it, so no one's having to reinvent the wheel, and that's where you end up losing a lot of time. Bit of a problem though is when you change it, you change the whole repo. You can't just change one little bit, you do have to push the whole thing again. So it is a bit coarse-grained, but that's not so bad. We know this version works. If you do a change and it breaks it, we're going back to the one that works. This is a bit of an idea of what that workflow would look like. So if we start at the top with your router and your config, your parser comes along, it scrapes up that state information and adds it to the Bender current state. It is this information that feeds both the config generation and our network monitoring. If it was going to our monitoring, it goes to our netlint agent to find when something is either changed or it's out of profile. It can send an alert to our Argus board. Argus is an alarm aggregation tool. Our counterpart in Norway created that. Again, it's open source, so help yourself to that if that's out there. And so what does the state look like? It's whatever you want it to be, but for us at this point, it's most of this operational output combined with the configurational output. It's only ever what you make of that state, what you ask of the routers. It's not going to be an exact copy of everything. And in the actual code, it just looks like a YAML file, as you would expect. Part of the reason of doing that is so when you migrate a service from, say, an MX80 to a ACX 7024, or even a completely different vendor, you can compare these two together before and after because you have made a network state that is comparable between the two. And so that's one of our key points about it. If you send it to the CLI tooling, you can make standardized config based on intent. And our previous speaker was saying about that as well. Such as, I want a VPLS between these two units, or I want to make a new core unit. The config on here is for a new core unit. The config is generated ahead of time. It's just put in as a text file, so that way you can just go into it and modify it if you need to. Sometimes there's always custom things that you might need to do, and you can do it ahead of time, so that way you're all set for your window before you actually have to apply anything. At least in this one, it has correctly added everything that we expect to be there. It's the class of service, the interface, it's on LDP, it's got the MPLS on the interface, it's got RSVP, got everything. And more importantly, it's picked up the addressing. It's gone to IPAM, it's assigned the address in IPAM so that no other engineer can take it from you before you've had a chance to apply it to the network and make it yours. There's quite a lot of times you'll probably find that you've allocated yourself something, but someone else has taken it and put it on the network before you did. So now you have to change it. It goes with our single source of truth that we're trying to find. We want the vendor network state and all this to be the one place for this truth. And it does it all faster than I can scrabble it together on a notepad and go into IPAM and assign the address. When we actually get to apply it and push it out, it does a couple of things. It will get an exclusive lock on all of the boxes that are doing it, so that way no other engineer can get in the way and interfere. Because it's a Juniper shop, it does bring up, we're just going to leverage the fact that it's got a show compare. It's got a perfectly good tool. We could do our own diff if we want, but if it's already there, well, don't wreck it. The engineer driving can assess, is the change correct? Is it changing the right interface and unit? It's not doing something that it really shouldn't be doing. And push them all out at once. Now, there is a bit of a risk in pushing changes out to all your boxes all at the same time. So we did build in some mechanisms like canarying, so that if you say, I want to change push to all 80 routers, it will actually stage how it's going to roll them out. It will only do on 2 of the boxes first, it will wait and slow down, a couple more boxes, and then it will finally get to the 3rd stage where it will actually go for the rest of the network. And parts of those checks are can you still actually reach the box? Can monitoring still reach the box? Cool. As long as you can do that, we can rechange it and we can fix it if there's something wrong. Later on, we might want to have kit from any other vendors, and this framework will allow us to do so, because we're building vendor neutral sort of information. So even later, if we move from Juniper to something else, we can compare their states and migrate afterwards. If we just roll that notes down a little bit. Or can I do that? Oh, there we go. Part of the state is, of course, the make and model of each device that you're pushing the changes to. That informs the config generator as to what type of config it should be generating. The config you make for an EVPN on an MX router is a bit different from an ACX router, and it needs to be able to put aside for you. The same canarying process would be created if another vendor's equipment was used. We just have to find another way to do it, because we're kind of leveraging commit confirmed at the moment, and that seems to be working quite well. After the configs are applied, we're back into the circle, and the parser will start scraping what has been applied, and then monitoring can tell you, are you missing something? Is the network still meshed? Has something else broken? That sort of thing. Has anything else gone awry as it was? And we've moved on to trusting it enough to be able to actually upgrade our boxes overnight without an engineer babysitting them. One of the consequences of also going from 30 or so to 80 boxes is if we need to do a firmware upgrade across the whole network, it's going to take 3 times as long. And in the past, that would be long nights by engineers. That's not going to scale. We're a small team of 6, and we're not likely to grow. There's not a lot of particular growth in these sectors, so we've got to work with what we've got. We've recently completed the first wave of updates. The initial selection, that still stays the same. That's still done manually. It's still tested in the lab. It's still rolled out by a single engineer. But they can use the automation to actually get the upgrade done in the first place so that it's being done in a consistent manner, consistent pre-checks, consistent post-checks. There's always a little bit of inconsistency between different engineers doing their upgrades. Some might pay more attention, some might not. So we want it to be exactly the same, plus have a record of what were the checks after. Maybe you don't notice the issue immediately afterwards, maybe you notice it in a few days. So it's good to have a good record of it. Same sort of canarying where we just start with a few boxes, and then eventually we start rolling out. Just roll that down a little bit more. There you go. During the full rollout, we get to the point where we do about 3 or 4 routers in the night with 1.5 hour blocks. We've also included a mechanism, because we're setting up a sequence of automated work, it needs to know to exit out as soon as there's been a failure, otherwise it's just going to keep cascading and making a mess of your network. So if you want to go through all the steps that it is doing, that's on the left-hand side. That's just upgrading one of our MX routers. And it took, an hour and 8 minutes for everything to happen. That includes the waiting for the box to do everything. So that's where a lot of that waiting comes from. One of the other tools we have is our MPLS Reoptimize. So if we cost a link, I can have this tool run around the network and quickly force all the LSPs to reoptimize and get off the link that I'm trying to drain. So I can do that in a couple of minutes. It's these sorts of tools that really made me start appreciating a bit more of the automation. I prefer, you might see a bit more old school, Notepad and CLI. I'm pretty sure I can do everything I need to. That's not the case anymore. If you want to be able to compete, if you want to be able to keep up, you'll need to be able to use some automation to improve both the accuracy of your changes, so it's actually happening, and the volume of changes that you need to be able to do. And part of the reason I think I was reluctant was it's a black box when you initially introduced to automation. It'll do everything you need and it won't break. But what if I'm in a change and it breaks? I'm up a creek with a paddle, I don't understand how it works. And that's not a situation I'm particularly comfortable with. But as time has gone on, I've become more aware of exactly how Bender works, so I can troubleshoot it a bit better. And so it's paying a bit more dividends now, in that I don't really need to do late nights babysitting network upgrades. I can just let it go through. If something happens, that's the on-calls problem. They'll be called and they can figure it out. Now, to be fair, I was on call in the first one. I wasn't going to be that mean to them. But that's what will happen. If it falls out of its window, on-call gets called and they've got to fix it. I think we only had one failure, and it just meant our engineer in Auckland suddenly had to drive to Hamilton. But that wasn't the automation's fault. That was the router in question. Having these sort of tools run around the network, running post checks, putting that in front of you within seconds and minutes, it gives the engineer more time to do what the automation can't, think. That's my chat for today. Thanks for listening to me. Did you have any questions, or did you just want to go to the pub? No? No, okay. I was worried Jeff was going to give me a question. Now I'm worried Tim was going to give me a question.
It's not so bad. Great talk, thank you so much. Question about Bender specifically. How does it model the configuration? Is it template files that's linked to the intent names? So adding a new vendor is just a new template plus the intent, or is there actually a structured storage for the configuration?
I should say that is my understanding of it. I can operate the thing, but I can't build the thing.
Okay.
So I'm just a humble data plumber. These sort of tools I'm just still learning, but that's my understanding of how you build each of the templates for the specific Mac models and configurations that you're trying to do.
Follow-up question. You mentioned a bunch of open source tools during your presentation. Will this be open sourced?
Probably not. It's highly specific at this point. If it was something, we would be open to it, just like with Romata. The community gives a lot to us, and we want to be able to give back to the community, and that's one way we can do these things. So, cool. All right. Thank you very much.
All right, so that's a wrap for day one. Just a reminder, buses are leaving at 5:30 from outside the conference at Armour Street. So you can drop your bags at the hotel, or alternatively leave it with the reception downstairs. For tomorrow, for those that are checking out, you can also leave it downstairs at the reception. Just FYI that the dinner tonight is pretty full, so for those of you that are very lucky, just a reminder to bring your badge, because that's very important for entry. And again, for the lucky winners of the remaining iPhone, so the numbers are 489 and 364, so please see the Mercury lady to get your new phone. Other than that, it's been a very good day one, and looking forward to another round of discussions tomorrow. Don't drink too much. Thank you.